Hi, and welcome to this course, which is an introduction to blockchain and Ethereum. Let us begin by taking a look at some of the prerequisites for this course. First of all, you should have some fundamental understanding of distributed computing. A blockchain network is effectively a distributed network of machines, so knowing some of the concepts behind that will help you really understand the course a lot better. Also, it is assumed that you have some knowledge of data structures and other computer science fundamentals. This is because blockchain technologies implement several different concepts and techniques, and it will be impossible to cover each of them in depth during this course. So, having some knowledge in advance will certainly help. And finally, familiarity with application development is not necessary, but will certainly be very helpful when we discuss the notion of smart contracts in Ethereum. So, that covers the prerequisites for this course. But before we proceed with the course material itself, I just have one tip. Learning about blockchains and Ethereum will involve getting familiar with many new terms. These can get a little overwhelming if we move a little too quickly, which is why the best way to understand exactly what each of those terms represent is by reinforcement. This is why I will try my best during this course to reinforce certain terms which had been introduced previously, especially if that becomes a fundamental building block to explaining a new concept. And with that, we can now proceed with learning about blockchains and Ethereum. To start off, let us take a look at the definitions of some of the common terms. First of all, what exactly is Ethereum? Well, this is a decentralized, open source, and public blockchain based platform which features the functionality of smart contracts. Many of these terms may not make sense without context, and we will be revisiting this definition just a little later. But remember that one of the most important features of Ethereum is the fact that it supports smart contracts. So we now move on to the next term whose definition we have, and this is what exactly a smart contract is. This can be thought of as a protocol to digitally specify, verify, or enforce the terms of a contract. It is in fact easiest to think of a smart contract as a regular contract which has been written in code rather than using some legal terms. In addition, the code may also specify some means of enforcing the terms of the contract without any human intervention. We now move on to another term in Ethereum, and this is the Ethereum virtual machine. I had mentioned earlier that a blockchain network is made up of a number of interconnected machines. All of these machines are referred to as nodes, and in the Ethereum blockchain network, each of these nodes will run a special software known as the Ethereum virtual machine. It is the Ethereum virtual machine which enables the execution of the smart contract code. So now we have discussed a few terms which are very specific to the Ethereum blockchain network. But let us now zoom out a little bit to a more generic term and then define what exactly a blockchain is. So a blockchain, if you're not familiar with it, can be thought of as a list of records, and these records are stored across a sequence of blocks which are chained together using cryptography. So there are once again a few different things mentioned over here. So let us break down this definition into its components to understand exactly what a blockchain is. First of all, it is a list of records. These records are split up and then stored across a sequence of blocks, and these blocks are maintained in a sequence by being chained together. We can now zoom in on each of these properties, starting with the fact that a blockchain is a list of records. So consider that we have a list of records. These can be thought of as the rows which make up a table, and this can in fact contain any data which you choose to store in them. Here, they are arranged in a sequence from 0 through 8, so we have a total of 9 records. The question now is, how can we store this data? One way to store this data is in the form of a table in a relational database. Another way to store this information is in a blockchain, and when this approach is used, the data will need to be stored across a sequence of blocks. So how exactly might this work for our list of records? Well, Consider that our 9 records are split into 3 different blocks. So we have 3 records in each of these blocks. And also notice over here that within each of these 3 blocks, the sequence of the records is maintained. However, in order to maintain an overall sequence of all of the records from 0 through 8, we need to ensure that there is a sequence of blocks as well. And this is precisely why we need to chain the blocks together in order to enforce that sequence. So when we have our 9 records split into 3 different blocks, we can enforce an ordering of these blocks by chaining them together. So to ensure that the block on the left precedes the block in the middle, we can establish a chain link here. And then to add a third block to this chain, we will simply append it to the end of the existing chain. This chaining is implemented by including a cryptographic hash of the previous block in every new block which is added to the blockchain. Later in this course, we will cover how exactly that is done. As new records keep getting created, we can provision new blocks and add those records to them, and then we can go ahead and add those blocks to the end of the existing chain. Each new block which is created will have a link to the previous block, thus ensuring an ordering of the blocks in the blockchain. So you can almost think of such a blockchain as a linked list structure. However, there are a few important characteristics of any blockchain. One of these is that it is a continuously growing chain. One must assume that new records will constantly be added to the blockchain, and there must be a mechanism in place in order to handle that ever-growing list. Another is the fact that this blockchain is not maintained by a single machine, but in fact by a network of nodes. And while the size of the network can vary, the number of nodes in the Ethereum network at the time of this recording is about 25,000. And when we have such a large number of nodes in a network, there must be some mechanism for them to reach a consensus on what the state of the blockchain should be. These are implemented in different ways on different blockchain networks, and we will cover how exactly this is done in Ethereum a little later in this course. Another very important feature of blockchain is that the records which are contained within them are immutable. This means that once a record has been added to a blockchain, it cannot be edited or removed. This is an important security feature of a blockchain network, which ensures full transparency to all of the participants. There are mechanisms in place to ensure that anyone trying to alter the records will be caught and will incur a cost for breaking the rules. So while this covers the prevention of fraud once a record has been added to the blockchain, there are also systems in place to ensure that any record which gets added to the blockchain in the first place is verified first. So while I mentioned previously that a blockchain can be thought of in some ways as a linked list of records, you can now see that that particular statement encompasses just one property of a blockchain. It is the properties which you see in front of you which truly define how unique blockchains are as a way of storing records. We saw in the previous clip that a blockchain can be thought of as a list of records which are stored across a sequence of blocks, and the sequence of these blocks is ensured by chaining them together using cryptography. So while that describes in generic terms what a blockchain is, let us now move into a specific example of a blockchain network, and this is the Ethereum network. Ethereum, as I had touched upon earlier, is a decentralized, open source, and public blockchain based platform, and this supports the notion of smart contracts. So let us now understand this definition by breaking it down into its components. First of all, Ethereum is a decentralized network, which means that the blockchain is not stored and maintained by a single node, but by multiple nodes. At the time of this recording, there are about 25,000 nodes which participate in the Ethereum network. Another important feature is the fact that Ethereum's code is open source. So the code which implements the blockchain network is available for all to view, and this makes it more transparent than some of the other blockchain networks available. One more crucial feature of the Ethereum network is the fact that anybody can join the network as a node, which makes it a public blockchain network. So these three features which you see in front of you can also be used to describe the Bitcoin network and some of the other cryptocurrencies. But what separates Ethereum from them is the fact that it supports not merely transactions involving the transfer of cryptocurrency, but with the implementation of smart contracts, we can pretty much define any kind of transaction, ranging from the transfer of assets to the implementation of a voting system. If there is any transaction which you can define using code, then smart contracts will help you implement it. With that, let us now take a look at some of the characteristics which define the Ethereum network. First of all, this is very much a blockchain-based platform. This means that Ethereum is used to store a number of different records on a blockchain, and the specific contents of the records are Ethereum transactions. As with any record in a blockchain, these transactions in the Ethereum network are immutable and can be verified. The fact that Ethereum is open source means that there is a community of developers who are constantly making bug fixes and adding new features. So you can either join the community if you fulfill their criteria, or you can keep an eye out for the new features and their release cycles. Most people's involvement with Ethereum, however, will be to simply join the network as a node and then invoke transactions which will be defined in a smart contract. There are no restrictions in place on who can join the network. As long as you have the requisite hardware and software, you will be allowed to join, and we will cover later on how there are different levels of participation you can have within the network. Of course, when you open up the network so that anyone can participate in it, there will be instances where some nodes will try to bend the rules of the system. To prevent this from happening, there need to be mechanisms in place which allow participants to work with other nodes whom they do not trust. For this purpose, Ethereum implements something known as the proof of work consensus algorithm, and this is something we will cover in depth later on in this course. Since one of the distinguishing characteristics of the Ethereum network is the ability to run smart contracts, many of the participating nodes need to have the Ethereum virtual machine or EVM on their systems. The EVM allows nodes to execute smart contracts, and those of you who are familiar with Java programming can in fact think of the EVM as being similar to the Java virtual machine. While the JVM will allow you to run Java bytecode, the EVM will allow one to run Ethereum bytecode. Ethereum bytecode is what you obtain when you compile a smart contract. Which brings us back to what a smart contract is. As we had discussed earlier, this can be thought of as a protocol to digitally specify, verify, or even enforce the terms of a contract. We can now dig a little deeper into what exactly a smart contract represents. So this is in fact a piece of executable code. There are a number of high-level programming languages in which smart contracts can be defined, and then they can be compiled to an executable form which can be executed on the Ethereum virtual machine. The code of the smart contract will represent specific contractual clauses. For example, if an interest amount needs to be paid out to deposit holders in a bank, the value of the interest payment as well as the timing of it can be defined within the contractual terms. The smart contract itself will not be private, but in fact will be deployed to the Ethereum network and will be available for all to see. And while the smart contract can be defined in such a way that not everyone will be able to invoke transactions from it, the code itself will be publicly available. An important feature of smart contracts is that they need not involve any human interaction. They can be defined to be self-executing as well as self-enforcing. And an important thing to keep in mind is that when you call functions which have been defined within the smart contract, if those functions happen to change the state of the blockchain or the smart contract itself, then a transaction will be invoked. In the example I just cited, transferring over interest payments to account holders will constitute a transaction, and the contents of these transactions will be stored as records on the Ethereum blockchain. In the previous clip, we discussed the fact that transactions which are invoked from a smart contract will be stored as records on the Ethereum blockchain. So what exactly is the mechanism of adding transactions to the Ethereum blockchain? Well, this brings us to the concept of mining, and this is something which can specifically be defined as the process of solving a complex mathematical puzzle in order to earn the privilege of adding a block of transactions to the Ethereum blockchain. We had touched upon the fact earlier that there are mechanisms in place to ensure that all participating nodes in the Ethereum network can arrive at a consensus on what the state of the blockchain should be. Since the state of the blockchain is defined by the contents of the transactions within them, Ethereum has a system where nodes can participate in mining. That is, they enter into a competition to see who earns the privilege of writing the next block of transactions. We had also touched upon the fact that before any record or transaction gets added to the blockchain, it needs to be verified first. This is something which is done during the mining phase, and as you can imagine, verifying a large number of transactions can involve the use of significant computing resources. As a result, mining nodes can incur very high electricity costs, for example, in addition to maintaining all of their hardware, and because of that, they need to be compensated in some form. And how exactly are they compensated? Well, they are paid in a cryptocurrency known as Ether. So, Ether is pretty much the crypto fuel for the Ethereum network. So, Ether is the cryptocurrency for Ethereum. And what distinguishes Ether from other cryptocurrencies such as Bitcoin is that the Ethereum network does not exist for the sole purpose of simply transferring Ether from one account to another, but Ether is used simply to pay out fees for transactions which are invoked from custom smart contracts. Ether does have a number of subunits which have been defined, but the most common ones you'll come across are the Way subunit, and it's 10 to the power 18 Way, which makes up 1 Ether. A less granular unit is the Gigaway, and it's 10 to the power 9 Gigaway, which makes up 1 Ether. So while you may pay for Ethereum transactions in terms of Ether, if you're running a business, you would like to know what that translates to in terms of either US dollars or euros or whatever your local currency is. And Ether can in fact be traded for regular currencies. At the time of this recording, 1 Ether could be purchased on the markets for about 130 US dollars. So while the US dollar and the euro are the currencies which are accepted as legal tender in the United States and the Eurozone respectively, Ether is the currency which is used in the world of Ethereum. And Ether payments are always required when a new transaction is originated on the network. Ether is transferred from the account of the transaction originator to the account of the miner who successfully mines the block with that transaction. And this Ether fee is in fact proportional to the complexity of the transaction. This complexity is measured in a unit known as gas. In this clip, we will explore how blockchains ensure that all of the records which are stored within them are immutable and verifiable. So for that, let us take a look at some records which are stored in a blockchain, and these, as you can see, have been split into a number of different blocks. In order to ensure a sequencing of the blocks, these are in fact chained together, and it is the mechanism of this chaining which ensures not only an ordering of the blocks, but also the immutability and verifiability of the records within them. So what exactly is this mechanism? How exactly is the relationship between adjacent blocks in a blockchain defined? Well, the answer to that is simple. There is a cryptographic link between adjacent chains. So each block in a blockchain includes a cryptographic hash of the previous block. In addition, it can also contain a timestamp for when the block was added to the blockchain. And of course, in the case of Ethereum, it includes all of the transaction data. If any individual transaction which makes up a block has been modified, then the hash of that block will be very different from what it was previously. In this way, the cryptographic link between adjacent blocks will be broken. So it is thanks to this cryptographic link that any transaction data which has been written into the blockchain cannot be modified after the fact. Any node can try to verify the entire blockchain by producing a hash of the very first block and then making sure that those hash contents are present in the second block, and then keep repeating this process until all of the blocks have been verified. If you wanted to change the contents of one transaction in one of the previous blocks in the blockchain, then you'll need to recompute the hash for that block, and then you'll need to include that modified block hash in the next block as well. For the next block, if the hash of the previous block has changed, then its own block hash will be different. So the hash for that block will also need to be recomputed. In fact, if you wish to change any of the previous transactions written to the blockchain, you will need to recompute the hash for every single block. And this is something which is not trivial, because you will have to reach a consensus among all the nodes which participate in the blockchain network. Getting this consensus is almost impossible, which is why the use of this cryptographic link ensures that every single transaction in the blockchain is both verifiable and also immutable or permanent. Which is why we can also define a blockchain as a distributed ledger which can record transactions in a manner which is immutable and also verifiable. So let us break down this definition into its components. So a blockchain is a distributed ledger. A ledger can be considered to be any sequence of records, and the records which are stored in a blockchain are distributed across multiple nodes which participate in the blockchain network. As for the contents of these records, in the case of Ethereum and most public blockchain networks, this will record a collection of transactions. The properties of these transactions include the fact that they are immutable. Any change which is made to an already recorded transaction can be detected by other participants in the blockchain network. The nodes will then be able to disregard this change and stick with the original version of the transactions. The transaction information can also be verified. Not only will they be able to verify that the transaction has not been altered, we will soon see just a little later in this course how they can verify that a transaction is indeed a valid one before it gets added to the blockchain. But what we have covered in this clip is the fact that the immutability and the verifiability of the blockchain transactions have been assured thanks to the existence of the cryptographic link to the previous block, which is included in every block in the blockchain. In this clip, we will cover the concepts of Ethereum accounts and nodes. To start off though, let us fully understand what exactly a blockchain network is. To do that, we will start off with the concept of a centralized ledger. So assume that there are several records which need to be accessed by a number of different entities, and these records are stored in a ledger which is in a central location. All of the entities which need to access the data which is stored in this ledger will need to establish a connection to the node which is hosting it, and this will give them all the information which they need. One benefit of this approach lies in its sheer simplicity. There is just a single copy of the ledger to maintain, and there is no constant communication required between the nodes in order to ensure its consistency. There are, however, two drawbacks with this centralized ledger approach. First of all, the host which contains the central ledger represents a single point of failure. If that were to go down, all of the entities which need to access the data will have nothing to work with. Another issue is one of performance. If the central ledger happens to be in a very distant location, then there could be significant network latency in accessing the data from the central ledger. The solution to these limitations is to have a distributed ledger. This is where all of the entities which need access to that ledger will maintain their own copies of it. When this is done, there is no network latency involved in order to retrieve its information. However, in order to ensure the consistency of the ledger, that is, to make sure that the copy which each node is working with is the same which all of the other nodes have, well, in that case, these nodes need to constantly communicate with each other. So having a distributed ledger in a setup such as this one will ensure good performance, and there is no single point of failure. However, there is some overhead involved when it comes to ensuring the consistency of the ledger with the constant communication with the other nodes. And if the ledger of records which is being stored happens to be a blockchain, well, then what we have here is in fact a blockchain network. So aside from maintaining a copy of the distributed ledger, what do the nodes in an Ethereum network need to do? Well, they also need to have the Ethereum virtual machine, and this is what will allow them to execute smart contracts. So the responsibilities of the Ethereum virtual machine not only includes executing the smart contract code, but it will also need to calculate the transaction complexity, and this complexity is measured in terms of gas consumption. The calculation of the transaction complexity will determine the total value of the transaction fee which needs to be paid by the originator of the transaction. Since every transaction does involve a transaction fee, before any transaction is added to the Ethereum blockchain, there needs to be a verification in place to ensure that the transaction originator does have enough Ether to pay the transaction fee. There are a few other verification steps which also need to be performed, and all of these are handled by the Ethereum virtual machine. So the nodes which participate in the Ethereum network not only run the Ethereum virtual machine, but they are also associated with at least one pair of keys. One of these is a private key, and this is used to sign, that is, to encrypt transactions which originate in the node. For every private key, there is a corresponding public key, and these will be used to verify the sender's identity and also to decrypt the transactions. As the names imply, the private key of each node is kept private. These should not be given away to anyone, since this will be used in order to establish your own identity. The public key, on the other hand, will be used to verify one's identity, and this is something which can be made publicly available. A little later in this course, we will explain in greater detail how this key pair will be used. So with that, we now have an idea of what the nodes in the blockchain network consist of. Not only do they run the Ethereum virtual machine, which enables them to execute smart contract code, they will also be associated with at least one pair of keys. More generally speaking, however, these keys actually represent accounts in a blockchain network. Each account is linked with one private and one public key, and it is possible for there to be multiple key pairs or accounts associated with a single node. So if there is any transaction which needs to be initiated on the blockchain network, and for simplicity's sake, consider that there is a simple Ether transfer transaction. Assume that this transaction is being triggered by the node C, which needs to send some Ether over to the recipient, which is on node D. This Ether transfer transaction will in fact take place through the accounts belonging to each of these participants. And in fact, in order to invoke any transaction on the Ethereum network, you need to make use of an Ethereum account. A single node or a single individual may have multiple accounts associated with them, but in order to originate any transaction, they will need to make use of one of those accounts. And accounts in Ethereum can be of two different types. One of these are externally owned accounts, and these are the ones which are associated with individuals and nodes. The other type of accounts in Ethereum are contract accounts, and these accounts belong to smart contracts. So what exactly are the properties of each of these types of accounts? In the case of externally owned accounts, they will have an Ether balance, and this balance can be used in order to invoke transactions. While transactions can involve the transfer of Ether from one account to another, even triggering the code in a smart contract can involve a transaction. In any case, there is a transaction fee which needs to be paid, and that fee will be deducted from the account's Ether balance. Each externally owned account in Ethereum is defined by its private key, and there is a corresponding public key which is associated with that and will be publicly available. One feature which distinguishes externally owned accounts from the contract accounts is the fact that there is no code which is associated with EOAs. These accounts also have an associated account nonce, and this is effectively a count of the number of transactions which have been invoked from the account. We will see exactly why this is useful a little later in this course. Moving along now to contract accounts, which are associated with smart contracts. These can also have an Ether balance. That is, you can load a smart contract with Ether as well. As you can imagine, there is code associated with a contract account, and the smart contract code can be executed by the Ethereum virtual machine. Running the contract code may not only add a new transaction to the blockchain, but may also modify the state of the contract itself. For example, a contract may include a function to transfer some of its own Ether balance to another account. So with that, we now have an idea of the two different types of accounts which are available in Ethereum. Externally owned accounts, which are typically associated with individuals and nodes, and contract accounts, which store the data for smart contracts. In this clip, we will take a closer look at transactions in the Ethereum network. So we have studied the fact that a blockchain can be thought of as a list of records. These records are split up and then stored in a sequence of blocks, and the sequencing of the blocks is done by chaining them together using cryptography. So if we have 9 different records which have been split up into 3 blocks as shown over here, these blocks in turn can be sequenced by chaining them together. The question now is, what exactly is contained within the records which are stored on the blockchain? In most cases, the answer is transaction information. To understand exactly what a transaction consists of, let us take a look at an example of a transaction. And while transactions in Ethereum can be rather complex, we will be considering one of the simplest transactions which can take place. This is where you have an entity C who wishes to transfer over some Ether to another entity D. Ether, you will recall, is the cryptocurrency which is used in the world of Ethereum. Now, any transaction which takes place in the Ethereum network involving the transfer of Ether will typically involve the transferring of Ether from one externally owned account to another. While it is possible to transfer Ether to and from contract accounts as well, let us stick to the example of 2 externally owned accounts involved on either side of an Ether transfer transaction. But very generally speaking, in Ethereum, any transaction typically involves the interaction between accounts. Even if you're making a call to a function which has been defined in a smart contract, this will involve you invoking a transaction from your own externally owned account to a contract account where the smart contract has been defined. In the case of a simple Ether transfer, on the other hand, this can be done by passing messages from one EOA to another in the network. So now that we know that it is accounts which lie on either side of a transaction, what exactly is contained within the transaction itself? First of all, there must be some recipient for the transaction. This could be an externally owned or contract account, and this recipient is identified by an address. Similarly, there is also the address of the sender which is included as part of the transaction. And in addition to both of these fields, there can be a value which is passed along with the transaction. This value could simply be a value of Ether which is being sent from the sender to the recipient. But with Ethereum smart contracts, it is also possible for one to define their own custom asset, and this could also be the value which is being transferred. Additionally, a transaction includes something known as a gas price. We have discussed previously that there is a transaction fee associated with any transaction in Ethereum, and this fee is proportional to the overall complexity of the transaction. This complexity is measured in a unit called gas, and the gas price field defines how much ether you're willing to pay for each gas unit. This determines the total transaction fee which you're willing to pay. However, the full gas cost of a transaction may not necessarily be known upfront, which is why you may find it necessary to specify a gas limit. This imposes a hard ceiling of the total transaction cost which will be incurred, and this also happens to be one of the fields which you can set when invoking a transaction. So now that we know that there are two accounts which are involved on either side of the transaction, and that there are a number of different fields which are included within the transaction body itself, the transaction will not be directly written to the blockchain, but in fact, a few additional steps need to be followed before that is done. Specifically, the transaction will first need to be processed, it then needs to be verified, and then added by all the nodes in the blockchain network to their individual copies of the blockchain. So going back to our sample transaction, we have the sender of the transaction, C, who wishes to send a total of 3 units of some asset to the recipient, D. The sender will invoke this transaction from their own node in the blockchain network, and this initialized transaction will then be broadcast to the entire network. While this transaction has been invoked, at the same time there will be hundreds, if not thousands, of additional transactions which will also have been initialized in the Ethereum network. All of these transactions are not processed immediately, but in fact will fall into an unverified transaction pool. So at some point, there will be thousands of these initiated but unverified and unprocessed transactions in this transaction pool. And then it becomes a question of picking up some, if not all, of these transactions for processing and verification. A subset of the transactions in this transaction pool will then be picked up and then ordered and then eventually added to the blockchain. However, there is a process which needs to be followed so that all of the participating nodes can arrive at a consensus on which transactions will get added to the next block in the blockchain and in what order. The way this works in Ethereum is that all of the participating nodes will pick up their own subset of these transactions from the pool and will have their own order of transactions. Out of those, one of the nodes will win the privilege of writing the next block of transactions, and the selection of that node happens through a process known as mining. Any node in the Ethereum network can participate in a competition to decide the next block to be written to the blockchain, and this competition involves solving of a complex mathematical puzzle. It is the winner of this competition who gets the privilege of writing the next block to the blockchain, and this includes the subset of the transactions which that node has picked up from the transaction pool and the order in which they have processed them. In the previous clip, we saw that any transactions which are initiated in Ethereum will fall into an unverified transaction pool, and then there will be a process of mining which will determine which of those transactions get added to the next block in the blockchain and in what order. In this clip, we will talk about the process of mining and the concept of gas, which is closely linked to it. So when a transaction has been initiated in Ethereum, there is no guarantee that it will be picked up in the next few blocks and then added to the blockchain. So there needs to be some kind of incentive for the mining nodes to pick up a transaction and process it. And this can be done by the one invoking the transaction by promising to pay a higher transaction fee. So once a transaction has been initialized and then thrown into the transaction pool, only a subset of these transactions will actually be processed in each block. So which of the transactions will fall into that subset? Well, before we answer that conclusively, let us introduce the concept of gas. Gas is a measure of the total computation work required in order to process a transaction. For any transaction which has been initiated in Ethereum, there will be a gas consumption number which will be available, and this will be an estimation of the total gas needed for the transaction to go through. So in addition to the gas consumption of a transaction, it is up to the transaction initiator to specify a gas price. So this determines how much the initiator of the transaction is willing to pay for each unit of gas which is required for the transaction to go through. Now, it is not always possible to determine exactly how much gas will be required for a transaction, and this is because a transaction may involve a number of different checks, and exactly what code is executed will depend on what the results of those checks are. As a result, it may not always be possible to determine exactly how much gas will be used in a transaction, and this is why it can be important to set a limit of the total gas which a transaction is allowed to consume. This gas limit is something which can be set by the one invoking the transaction. Now, what exactly determines how much gas will be used up by a transaction? Well, the answer to this is the Ethereum virtual machine, and this is something which every node involved in the mining of transactions will need to run. So EVM, as we have discussed previously, is a common runtime environment which is used to execute the smart contract code, and this is something which will also be able to verify transactions. Part of the verification process involves measuring the total gas consumption for the transaction, and this will be used to determine whether the initiator of the transaction has enough Ether in their accounts to pay for the transaction to go through. So the transaction initiator will have to pay a transaction fee which is proportional to the amount of gas consumed by the transaction they have invoked. And this transaction fee will end up in the account of the miner who has successfully mined that transaction. In fact, this is the reward for being a miner in the Ethereum network. Since mining involves running each transaction and verifying it, it does end up consuming significant computing resources, and miners need to be compensated for it in some way. And the way this happens is that they get to pocket the transaction fee which is associated with every transaction which is included in the block they have mined. The value of the fee for each transaction is a product of the gas consumed by the transaction and the gas price quoted by the transaction initiator. In addition to pocketing all of the transaction fees, a successful miner also gets to keep any newly minted Ether in each block. Like any cryptocurrency, new Ether is minted in each additional block which is added to the blockchain, and this new Ether makes its way into the account of the successful miner. So going back now to a transaction pool, where we have a collection of transactions which have been initiated but have not yet been verified. Out of all of these transactions, each miner will pick a subset, and to determine what subset of transactions to pick up, the miners will be taking a look at the gas price of each of these transactions. The higher the value of the gas price, the greater the transaction fee which the miner will stand to gain if they were to be the successful miner for the block. And this is precisely why the gas price field of the transaction becomes an important factor in determining how quickly it is processed by the network. Do keep in mind, however, that every single miner in the network will have their own subset of transactions, and each of these subsets are likely to have significant overlaps. Once a miner has picked up a transaction for processing, however, there still needs to be a verification process. During the verification, a number of different checks are performed, including verifying the identity of the sender. Another detail which needs to be checked is that the transaction has not been modified in any way after being initiated by the sender. Each of these steps involves the use of the private and public key pair which belongs to the account which invoked the transaction. And we will see a little later in this course the exact mechanics of that. And in addition to these two verification steps, there also needs to be a check to ensure that the transaction initiator does indeed possess the assets which they are transferring over in the transaction. This will also involve checking, for example, whether the transaction initiator has enough ether to pay for the transaction to go through completely. So every miner will have picked up their own subset of transactions from the transaction pool and then will verify every single transaction which they have picked up. However, at this point, every single mining node has its own set of transactions and in their own order. And given that Ethereum is a distributed system with thousands of different nodes, there needs to be some kind of consensus among these nodes on what the contents of the blockchain should be. So the specific points which the nodes need to agree upon include the contents of each of the transactions and also the total ordering of the transactions. So how exactly do all of these nodes arrive at a consensus? One of the complications of arriving at a consensus in a public blockchain network like Ethereum is the fact that the nodes must come to an agreement even though they don't entirely trust each other. For this to happen, the solution is a systematic one where the system must ensure that any malicious actors are not rewarded for their behavior. And how exactly is this achieved? Well, by the means of consensus algorithms. And when it comes to Ethereum, there are two different consensus algorithms to discuss. One of these is the proof of work consensus algorithm, which is the one which Ethereum started off with and is still currently in use at the time of this recording. However, there have been discussions going on for a number of months about migrating to a proof of stake consensus algorithm. Both of these will be discussed a little later in this course. In this exercise, you will first enumerate some characteristics of blockchains. We have covered during this course that blockchains can be used to store records across a number of different blocks which have been chained together in a sequence. In addition to that, there are various properties of blockchains which make them an ideal structure in which to store data in a transparent manner. You will need to recall what some of those characteristics are. While that covers the properties of blockchains in general, for the next task in the exercise, you will identify some attributes of Ethereum. Ethereum is one of the most widely used blockchain networks out there, and there are various reasons why this is the case. You may recollect what those are and then list them down. For the next task, you will note down the two types of Ethereum accounts. Any transaction which is invoked in the Ethereum network needs to be done through an Ethereum account. There are, however, two types of accounts available in Ethereum, so you need to mention what those are and what each of their specific properties are as well. For the next task, you will detail each of the constituents of an Ethereum transaction. When a transaction has been initiated in the Ethereum network, there are several details which are included within the transaction body. You will identify exactly what those are and what purpose they serve. And for the final task in the exercise, you will enumerate the rewards which a node may receive for successfully mining transactions. All of the mining nodes in the Ethereum network will enter into a competition to see which one of them gets to write the next block of transactions to the Ethereum blockchain. The reason they enter into this race in the first place is to reap the mining rewards, and you will need to identify what exactly those rewards are. All of these topics were covered during this course, so please pause this video and then take some time to perform this exercise on your own. For the first task in the exercise, you needed to recall some of the characteristics of blockchains. Blockchains are a very useful data structure in which to store records. In the case of the Ethereum network, for example, the records contain details of transactions. Given that transactions in the Ethereum network are not static and are continuously being generated, it is necessary for the data structure recording those transactions to be able to grow continuously and in an unbounded manner. This is exactly what a blockchain is capable of and what makes this the ideal data structure in which to record transactions. In addition, There is not just one node which is responsible for storing and maintaining the blockchain. There is, in fact, a network of nodes which are tasked with this responsibility. As a result, blockchains represent a distributed ledger of records, and each participating node can maintain its own copy. This means that there is no single point of failure when it comes to the blockchain, since there will be several copies floating around in the network. However, when there is an entire team of nodes involved in maintaining the blockchain, there needs to be some mechanism in place for those nodes to arrive at a consensus on what the state of the blockchain should be. This is why all blockchain implementations have a consensus algorithm. In the case of the Ethereum network, this is the proof of work algorithm. An important property of blockchains is that the records which are stored on them are immutable. Once a record has been written into the blockchain, there is no way for someone to go and edit it or even remove it. It is this transparency which enables participants in a blockchain network who do not entirely trust each other to still work together. Now, if someone does try to go ahead and alter one of the records written in the blockchain, then this action can be rather easily caught, and this is because every record which is written to the blockchain can be verified. This may involve having to replace some transactions and recreating some blocks, but it is this verifiability of records which allows participants to work together in a trustless environment. For the next task, you needed to enumerate some of the characteristics of the Ethereum network. So Ethereum, as we have seen, is a blockchain-based platform, and this happens to be a public blockchain network. A public network is one which is open for entry, and anyone who has the requisite hardware and software will be able to join in the network without any vetting required prior to that. The code which runs the Ethereum network is also open sourced, and there is a community of developers who are constantly fixing bugs and adding in new features. Given that Ethereum is a public blockchain, there needs to be explicit mechanisms in place in order for untrusted nodes to work together. This is what Ethereum achieves by means of the proof of work consensus algorithm. And one of the most powerful and popular features of the Ethereum network is its support for the notion of smart contracts. These are in effect contracts which are written in code rather than in legal terms. And given the public nature of the Ethereum network, the smart contracts are available for all to see. For the next task, you needed to list down the two types of Ethereum accounts and their properties. One of these is the externally owned account, and these are the accounts which are typically associated with nodes or individual users. These accounts will possess an Ether balance and have the ability to invoke and send transactions. Since every transaction needs to be authenticated, each account will be associated with a public and private key pair. An externally owned account does not include any code. However, it does happen to be associated with an account nonce. This is effectively a transaction counter which is incremented by 1 for each transaction which is invoked from that account. The other type of Ethereum account is the contract account. This is what is used to represent every smart contract on the Ethereum network, and much like an EOA, this can also possess an Ether balance. That is, you can load a smart contract with Ether. As you would expect, a contract account does have code associated with it, and it is possible for the smart contract code to modify the state of the contract account, for example, by transferring some of its Ether out to some other account. For the next task in the exercise, you needed to note down the constituents of an Ethereum transaction. So whenever a transaction has been invoked in the Ethereum network, there is a transaction body which will contain a few fields. One of these is the address of the account of the sender of the transaction. The transaction will also have a recipient, and this could be a contract account or an externally owned account. And every transaction is associated with a value of assets which are being transferred from the sender to the recipient. In addition, one can also set a gas price in the transaction body, and this is effectively an incentive for the transaction to be picked up by one of the mining nodes. There is also a gas limit which can be set in a transaction, and this is done in order to impose a ceiling on the total transaction cost. And for the final task, you needed to recall the rewards which a node can receive for successfully mining a new block and adding it to the Ethereum blockchain. Well, the biggest constituent of the mining reward will be the transaction fees associated with every single transaction which is included in the block. For each transaction, the fee can be calculated as the gas used by the transaction multiplied by the gas price which was stated when invoking that transaction. For each new block which is added to the Ethereum blockchain, the network will produce new Ether, and these are also issued to the successful miner of the block. We have previously covered the fact that the immutability of the transactions in a blockchain is ensured by including a cryptographic hash of the previous block in each block of the blockchain. In this clip, we will see exactly what cryptographic hashing is and how this applies to blockchains. Before we delve into cryptographic hashing, however, let us revisit the definition of a blockchain. So this is a list of records which are stored across a sequence of blocks, and each of these blocks are chained together using cryptography. Breaking down this definition, we know that blockchains are a list of records, and we know that they are stored across a sequence of blocks. The part we will be focusing on in this clip is the fact that they are chained together using cryptography. So when we have a number of different records which are split across different blocks, and these blocks are chained together, how exactly is the relationship between adjacent blocks defined? Well, each block in the blockchain includes a cryptographic hash of the previous block. The block also includes a timestamp, and of course, it includes the transaction data in the case of Ethereum. The block can also include some metadata, and these are not the only fields which make up the block, and there are a few others as well which we won't get into. For now, this is enough for us to get a basic understanding of blockchains. We move along now to the concept of a hash algorithm. This is something you're probably familiar with already, but it doesn't hurt to revisit this concept. So, given an input message, if you pass this as an argument to a hash function, it produces an output which is typically of a fixed length, and this output is known as the hash value of the input message. We now focus on the hash value because you will have seen this in a number of different forms. This is because the hash value of any message is also known as a message digest, or very simply, a digest. Another term this is often referred to as is a digital fingerprint and also a checksum. If you have downloaded any large file from the internet, you may have often seen that a message digest or a checksum of the file is included. This is simply the hash value of the downloaded file, and it is used to check whether the downloaded file has been tampered with in any way during the download process. This is in fact precisely how it is used in blockchains as well, where the hash is used to check whether the blockchain has been altered in any way. So given that hashing has rather widespread uses, what are the ideal properties of a hash function? First of all, it should be rather easy to compute the hash of a given message, no matter what the size of the message, whether it is a few lines of text or even an entire book. Computing the hash value should be simple. Another desirable property is that the hash function should have a low probability of hash collisions. Hash collisions, in case you're not aware, is when two different input messages produce the same output hash value. Given that hash outputs are often of a fixed length, it is nearly impossible to define a hash function which will produce zero collisions. However, a good function will in fact produce very few of these. And while these are properties of a good hash function, when it comes to a cryptographic hash function, it has one additional property. So just like with regular hash functions, cryptographic hashes should be easy to compute and should have a low probability of producing a hash collision. But what makes these functions ideally suited for security is that it is nearly impossible for any malicious entity to view only the output hash value and then use that to recreate the original message. This is not typically a requirement of a normal hash function, but in the case of a cryptographic hash, such a property will ensure that any change which has been made to the input file will be noticed because it will have an entirely different cryptographic hash. So a cryptographic hash can be defined as a special hash function in which it is impossible to recreate the original message given only the output hash value. So like with a regular hash function, a cryptographic hash algorithm will take in an input message as an argument and will produce an output hash value. However, any attempt to recover the original input message given the hash value will result in a failure. So how exactly does this apply to blockchains? Well, we have covered the fact that each block within the blockchain will include a cryptographic hash of the previous block, and along with that, it can include other data such as the timestamp for the block, as well as all of the transactions which make up the block. Now, what is the specific cryptographic hash function which is used in blockchains? Well, in most instances, and definitely in the case of Ethereum, it is the SHA-256 algorithm. This has its origins in the SHA-2 algorithm, where SHA is short for Secure Hash Algorithm. This was originally designed by the National Security Agency in the United States, and the SHA-256 algorithm belongs to the SHA-2 family. The number 256 over here pertains to the number of bits which are produced in the hash output. To understand how this works, let us take a look at an example. Say we have input text, which is simply the word wind with an uppercase W. If we were to pass this word over to the SHA-256 algorithm, the output which will be generated will look like this. Now, given that we have this hash output, let us try to recover the original input message, and for that, we can try to feed this hash value back to the hash function. Now, we expect that this will not work, since given the hash output, it should be impossible to recover the original input message. But let us just try it out to see what will happen. So we can see here that this particular hash output for the word wind starts with the letters B1. Before we feed it into a SHA-256 hash generator, we take a look at these first two characters as well as the last two, which are C8. And what we get as output is completely different, which you can confirm by looking at the first two and the last two characters. In fact, even a minor change in the input will produce a completely different hash output. So we have here the hash output for the word wind, and once again keep an eye on the characters at the extremes. Now, if we were to modify the input to just be windy and then feed that into a SHA-256 algorithm, well, the output hash will be entirely different. The application of this is that any minor change which is made to a transaction in any of the blocks in the blockchain will produce an entirely different cryptographic hash. So any modification of the transactions will be easy to detect. One thing to keep in mind when it comes to using the SHA-256 algorithm is that the output hash will always be of a fixed length, irrespective of the size of the input. So, if you were to replace the text windy with a very large volume of text, perhaps even an entire book, the output which will be generated will be exactly 256 bits in length. This particular feature is in fact rather useful since it allows you to predict how much storage will be required for the hash value of any data. In the previous clip, we covered the concept of cryptographic hashing and how exactly it applies to a blockchain. In this clip, we will see why exactly a blockchain stores records as a chain of blocks rather than simply have one large list of records. So starting once again with the definition of a blockchain, we know that it is a list of records which are stored across a sequence of blocks, and that these blocks are chained together using cryptography. Now, a blockchain is in essence a list of records, and there is a specific word for this, which is a ledger. The blockchain stored by the Ethereum network is in fact a distributed list of records, which makes it a distributed ledger. And each of the records which are stored in this ledger are transactions. So just to visualize a distributed ledger, we start off by looking at a centralized one. So here we have a single ledger, which is accessible to a number of different nodes. This setup, however, represents a single point of failure, and there can also be significant network latency for all the nodes to retrieve the ledger data from a single source. The solution to this, of course, is to have a distributed ledger where each of the nodes participating in the network maintains their own copy of the ledger. If this were to happen, there is no single point of failure, and the nodes need not go over the network to access the ledger data. However, in order to ensure that the copies of the ledger are consistent with what the rest of the network has, the nodes will need to constantly communicate with each other. It is this communication to ensure the consistency of the ledger which we will now take a closer look at. So from these nodes in this network over here, let us take a reduced version of the network where we have three of the nodes in consideration. There is the node A, and this has a ledger which has a total of 1 million transactions. B has a similar ledger also with 1 million transactions, as does the node C. All of these three nodes will now need to ensure that they're working with the exact same copy of the ledger. What does that translate to? Well, they need to make sure that they have the exact same transactions and in the exact same order. So when working with a distributed ledger, we do not have a single point of failure, but these nodes need to be in constant communication to ensure that they're working with the exact same ledger. That is, the ledgers have the same transactions and in the same order. Now, how can these nodes figure out whether they're working with a different copy of the ledger? A trivial solution to that problem is to compare each of the ledgers line by line and then check for any inconsistencies. However, you can imagine that when the size of the ledger keeps growing, the time taken for such a comparison will also keep increasing. So this is clearly not a scalable solution. This is especially true because most of the time, we expect that the ledgers will match. In addition, such an operation will involve each of the nodes in the network sending a copy of their respective ledgers to every other node. This will generate needless amounts of network traffic, and this is something which can be optimized by adopting the technique of hashing. So rather than each of the nodes sharing their entire ledger with every other node, they can simply hash their ledgers and then share their respective hashes with the other nodes. The nodes can then just compare their hashes, and then most of the time the hashes will match, and then no further action is necessary. Going back to our example now, where we have three different nodes, and each of them has a copy of a ledger which has 1 million transactions in total. The node A computes a hash of its own ledger and then comes up with a hash value. The node B will come up with its own hash, as does C. So when each of these three nodes share their hashes with all of the others, they will eventually come to realize that the node C happens to have a different hash when compared to the other nodes. So even if we were to expect that in most cases the hashes will match, in such a case when there is a mismatch, well, we simply need to iterate through each of the 1 million transactions and then determine where exactly there is a mismatch. In fact, a ledger with 1 million transactions is rather small, and in reality, you may even have one with billions of transactions. So once again, this search is not an efficient one, and there should be a further optimization which is possible. Well, this is exactly what is achieved if we can break up these transactions into a number of different blocks. In our example, consider that each of the nodes has broken up the 1 million transactions in their respective ledgers into 1000 blocks, each containing 1000 transactions. Now, rather than the node sharing a single hash with the other nodes, they will need to share 1000 hashes, one for each of their blocks. So once the sharing has been performed, if there is a mismatch detected in one of the hashes, well, in that case, they only need to examine the transactions in the mismatch block. This reduces the search operation to a total of 1000 transactions as compared to the 1 million transactions which needed to be checked previously. In most instances, it'll just be the most recent blocks which are checked for consistency. A comprehensive check involving all of the blocks can be performed less frequently. So by dividing the ledger into a number of different blocks and then using the hash values in order to compare the blocks, we have significantly optimized the checking for consistency. Since the overall ordering of the transactions is important, we need to ensure that the transactions are arranged in order not only within the blocks, but also as a whole. That is, we need to chain the blocks together into a sequence. And when we store our records across a number of different blocks which have been chained together, what we have is a blockchain. This chaining of the blocks is implemented by including a hash of each block in the next block in the blockchain. So in this particular blockchain, the second block includes the hash of the first block, and in turn, the third block includes the hash of the second block. However, the first block in this blockchain does not include a previous block hash since there is no previous block to speak of. So this is a special block in any blockchain and is referred to as the Genesis block. So this complete image here will give you an idea of what a blockchain looks like. Each block includes a set of transactions. In addition, it also includes a hash of the previous block, and it will also include some other information. This could include the block metadata, as well as some state information with regards to the accounts. Previously, we have covered how splitting up a large number of records into chains of blocks allows us to maintain an ordering of the records and then can also optimize any searches for individual records, especially in the cases of discrepancies between the ledgers of one node in the network and the others. In this clip, we will take a look at how that process can be further optimized by the use of a data structure known as Merkle trees. We begin by revisiting the ledger which is shared by all of the nodes in the network. Our network consists of 3 nodes, A, B, and C, and the ledger which they share has a total of 1 million transactions. It is not just the contents of the transactions which matters, but even their ordering. And in order to ensure that all of the nodes are working with the same copy of the ledger, they will need to verify that they each have the same transactions and ordering. We saw how this process can be optimized to some degree by splitting up the ledger into multiple blocks. We then calculate the hash values of each of those blocks, and the nodes can then exchange the block hashes and then compare each of those. As an example, consider the node B, which has broken up its ledger of 1 million records into 1000 blocks of 1000 transactions each. The hashes of each of those blocks have been computed, and then all of the nodes share their block hashes with each other. Now, if one of the nodes were to do a comparison of their block hashes with the others, then they may eventually realize that one of their blocks is inconsistent with the other nodes. So after the nodes A, B, and C have shared their block hashes, the node B realizes that its hash for the block number 500 is different from that of the other nodes. Now, in order to investigate which of the records in block number 500 is the root of the discrepancy, we simply need to scan through all of the records in that particular block, which means that the 1000 transactions in block number 500 will need to be compared with that of the other nodes. This is significantly more efficient than had we not split up the records into blocks. In that case, we would have to scan through 1 million transactions rather than 1000. So now let us take a closer look at block number 500 for each of the nodes in our network. Block A has computed a certain hash value. Block B has a different hash value for the same block. And block C has the same hash as block A, but different from that of block B. We can see over here that this particular transaction within B's block is different from that in the other nodes. And the property of hash functions is that even if there is a slight mismatch in the input to the hash function, the output can be completely different. Now, in order to identify the exact source of the mismatch, one will need to scan through the entire block. And while this is definitely more efficient than having to scan through the entire ledger if it hadn't been broken up into individual blocks, this is still something which leaves room for optimization. So a problem over here is to find a mismatched transaction in an ordered set of records. If these records are represented as a list, then this is a problem with the complexity of big O of n. That is, the time taken for the search is directly proportional to the number of records among which we need to conduct that search. This operation can be improved if we were to represent the transactions not as a list, but as a tree structure. In this case, the complexity of the search becomes big O of log n rather than big O of n. That is, the time taken for the search is directly proportional to the log of the number of records. So how exactly can we represent the transactions in a block as a tree data structure? Well, in order to obtain this O of log n complexity, we can record the transactions in the blockchain in the form of a special data structure known as a Merkle tree. So what exactly is a Merkle tree? So this is a tree data structure in which every leaf node is labeled with the hash of a block of data, and every non-leaf node is labeled with the cryptographic hash of the labels of its children. So assuming that we have 4 transactions in a block, these are transactions A, B, X, and Y, then this is the Merkle tree representation of those transactions. The leaf nodes at the bottom represent the transaction data itself, and then each of the non-leaf nodes represent the hash of their children. At the very top, there is the root node of this tree structure, and this is known as the Merkle root. But in order to understand exactly how this Merkle tree is constructed, we begin with just our transaction data. Now remember that in a blockchain, it's not just the transactions themselves which are important, it's also the ordering of these transactions which matters. So we have the transactions in the order A, B, X, and Y. The first step towards building the Merkle tree for these transactions is to compute the hash of each of these transactions. So we now end up with 4 hashes, and following that, we will break up these hashes into pairs and then produce a combined hash of those pairs. So the hashes of A and B have been combined to produce a hash AB, and similarly, the hashes of transactions X and Y have been combined to produce the node hash XY. Do keep in mind that the ordering of the transactions is captured here, since the hash of AB will be different from the hash of BA. We repeat this process once more, and we produce a combined hash of AB and XY, which is hash ABXY. In our case, this becomes the root of the Merkle tree. And this Merkle root is something which is stored separately within a block. Now, this is what our Merkle tree structure looks like when we only have 4 transactions in all. The more transactions we have, the greater the size of the Merkle tree structure. Now, given that the Merkle root will be stored within each block of the blockchain, the nodes in the network can compare the Merkle root of each of the blocks in order to check for inconsistencies. As an example, consider that it is transaction X which is the source of the mismatch. Now, rather than scan through each and every transaction in a block, you only need to go through a part of the Merkle tree in order to identify the source. So for instance, a node may realize that its Merkle root is different from that of the other nodes, so it will take a look at each of its children. It will notice that the hash of AB is the same as that of the other nodes, but the hash of XY is a mismatch, and that is the path it will choose to investigate further. Looking at the two children of hash xy, it will realize that it is the hash of x which is a mismatch, which means that it is transaction x which is the root of the problem. So, by storing all of the transactions in a block in the form of a Merkle tree structure, a blockchain network is able to capture the entire state of the block, and by doing that for all of the blocks, it is able to capture all of the transactions in the ledger. In the case of the Ethereum network, all of the mining nodes will compute this Merkle tree while they are verifying the transactions to add to a block. We also saw that the Merkle tree representation not only captures the contents of the transactions, but its ordering as well. And in case there are inconsistencies between a particular block on one node and that of the others, then identifying the transaction at the heart of that mismatch becomes a binary search rather than a linear search. Previously in this course, we have seen how transactions once initiated by a sender get thrown into a transaction pool, and then a miner will pick it up and then verify the transaction before including it in a block to be added to the blockchain. In this clip, we will focus on one particular aspect of the transaction verification process, which is verifying the identity of the sender. So let us begin by taking a look at the transaction verification process. So once a transaction has been initiated, it gets thrown into an unconfirmed transaction pool. All of the mining nodes in the blockchain network will then pick up a subset of these transactions and will then create their own individual blocks, which will become candidates to be added to the next block in the blockchain. However, one of the requirements for any transaction which will get added to the blockchain is that it should successfully go through a verification process. So let us now take a look at what goes on during this process. There are two very important things which should be covered during the verification. First of all, the identity of the transaction initiator and the integrity of the transaction which is in the transaction pool do need to be confirmed. This is to ensure that the transaction which is in the pool has not been tampered with in any way. The exact mechanics of this verification is something we will take a look at in the next clip. Another thing to verify is that if the sender is transferring over some ether to a recipient, then that the sender does indeed possess enough ether for the transfer to take place. In the case of the Ethereum network, this information is available in the state information for an account. Another piece of information which is available in the state and which is used in the transaction verification process is the transaction nonce. This is effectively a serial number which counts the number of transactions which have been initiated from an account in Ethereum. This is useful to confirm that a particular transaction which is available in the transaction pool is not simply a replay of an old transaction and is in fact a newly minted one. As touched upon, both of these checks which are highlighted here are something which can be done by taking a look at the state of the accounts in Ethereum. So let us now take a look at how transactions are initiated, how they are picked up, and then how they get verified. So assume we have multiple nodes in the blockchain network. In this particular case, there are a total of 6 nodes. And one of these nodes happens to be a sender of a transaction, that is the transaction initiator. So let us say node C wants to send over some ether to node D, which is the recipient in the transaction. So in simple terms, node C simply wants to send over some ether to node D. In the context of the entire blockchain network, this transaction could happen on a one-to-one basis. So the sender will use their account to initiate the transaction from node C, and this transaction could make its way directly to node D in the network, which belongs to the recipient of the transaction. In simplified form, the transaction body includes the sender C, the recipient D, as well as the value of the asset being transferred. In reality, both the sender and the recipient will be identified by their account addresses. And the transaction body will not only include these 3 fields, but will also include a gas price as well as a gas limit. But let us stick to this simplified form for the rest of this example. Now, even though this transaction only directly concerns two of the members of the blockchain network, it will in fact be broadcast to every single node in the network. So it is not just node C and D, but all of the nodes which will get a copy of this transaction. So while we have only been talking about a single transaction now being broadcast to the entire network, in a real blockchain network such as the main Ethereum network, there will in fact be multiple, that is perhaps thousands of transactions which are broadcast simultaneously to every single node in the network. When there are so many different nodes and so many different transactions involved, it is important for all the participating nodes in the network to arrive at a consensus. So when you have several transactions, potentially thousands of them, which have been broadcast to the network and then thrown into the transaction pool, many of the miners will pick up some subset of these transactions. Many of these subsets will have significant overlaps in terms of the transactions itself which have been picked up. However, what will vary considerably in the sets for each of the miners is the ordering of the transactions. So while the thousands of miners in a network such as Ethereum will have their own sets and ordering of transactions, it is important for all of these nodes to arrive at a consensus on what the correct state of the blockchain network should be. And this is something which is done by means of a consensus algorithm. But before this algorithm can be applied, every miner will need to ensure that the transactions which they have picked up from the transaction pool are valid ones. For that, they'll need to go through a verification process for each of those transactions. And it is the steps in the verification process which we will now take a closer look at. One of the steps in the transaction verification process is verifying the identity of the transaction initiator. Any transaction which is invoked in the Ethereum network must happen through an account. Every account is identified by means of a key pair. Every key pair includes a private key, which is similar to an ATM PIN and needs to be kept private by the account owner. Every private key has a complementary public key, and this in many ways is similar to the CVV number which you find at the back of a credit card or a debit card. So the private key is something which needs to be kept private, and it maps to a public key which can be shared with others in the network. It is the combination of these two which will be used to verify the identity of any transaction initiator in the Ethereum network. But how exactly does that work? Well, when any sender invokes a transaction in the Ethereum network, they are sending across not one, but two messages. One of these is the digitally signed version of the transaction body. So this is where the transaction contents have been taken and then encrypted using the sender's private key. The other message which is sent across is the raw version of the transaction body, one that has not been signed. The purpose of sending across the digitally signed message along with its raw contents serves these three purposes. One of these is authentication. One can verify the identity of the sender of the transaction. The second is non-repudiation. Since this digitally signed message was encrypted using the private key of the sender will not be able to deny the fact that they initiated the transaction. And lastly, this digitally signed message will also confirm the integrity of the transaction. That is, one can rest assured that the transaction has not been tampered with in any way after it has been initiated by the sender. So just to quickly summarize, the use of a digitally signed message serves three purposes. Authentication is where the identity of the sender is confirmed. Non-repudiation ensures that the sender cannot deny having sent the transaction over. And integrity is where one can be assured that the message was not modified in any way during transmission from the sender to the transaction pool. Let us now delve into the mechanics of exactly how this works. So on the left, we have the sender side of the transaction, where the sender uses an encryption function whose inputs include the transaction hash as well as the private key of the sender. When both of these are combined, what we get as output is the signed version of the transaction. This signed transaction will then become an input to the decryption function, which is available at the recipient. And the decryption function's arguments include the signed transaction and the public key of the sender. Since the sender's public key is, well, public, it will be available to every node in the network. The encryption and decryption functions used over here are also common ones which will be available to all the nodes. So what does the decryption function output when these two arguments are passed into it? Well, this should give you the original transaction hash. The way digital signatures work, this transaction hash, which is available at the side of the recipient and is the output of the decryption function, should be exactly the same as the transaction hash which served as input to the encryption function on the side of the sender. This is provided that the sender's private key on the encryption side and the public key used on the decryption side are complementary. And if there is a match of this transaction hash, then the recipient has the confirmation was signed using the private key of the sender. In this way, they know that it was the sender who sent the original transaction, so they have been authenticated, and they cannot repudiate the fact that they initiated the transaction. In addition, the integrity of the transaction can also be confirmed. However, for that to happen, the sender will also need to send across the unsigned version of the transaction to the recipient so that the recipient can then generate a hash of this transaction and then compare it to the transaction hash which was output by that decryption function. Let us take a look at the entire process by means of this workflow over here. So on the left, we have the sender side of the workflow, and on the right, we have the workflow at the recipient's end. The sender takes the raw transaction data and then passes it into a hashing function, which will produce this transaction hash. This hashing function will be something like the SHA-256 hash, which is available to the general public. This transaction hash, along with the private key of the sender, is passed as argument to an encryption function, and the output of that function is the signed version of the transaction. This signed transaction is now sent over to the recipient along with the raw transaction body, which is neither hashed nor signed. At this point, the recipient has two pieces of information which have been transmitted by the sender, the raw transaction body as well as the signed version of the transaction. The recipient has another piece of information available to them though, which is the public key of the sender, and this is something which is publicly available. Both the signed transaction and the public key become the inputs to the decryption function, and the output of this function should produce the original transaction hash as long as the transaction is an authentic one. So the way to confirm that this is the original transaction hash is to use the final piece of information which is available to the recipient, which is the raw transaction body. This is fed as input to the hashing function, which the recipient also has, and this will produce a transaction hash. If both the transaction hashes available to the recipient are a perfect match, it means that the transaction has been successfully verified. So this verification, as we know, has covered three different aspects. One of these is authentication, because we now know that the transaction was signed by the sender's private key, and we assume that they are the only ones in possession of it. At this point, the sender cannot deny that they sent over the transaction in the first place because their signature is on that transaction. And the recipient also knows that this transaction body has not been tampered with in any way because the raw transaction matches the decrypted transaction which has been recovered. So these cover just some of the verification steps which need to be performed for any transaction in Ethereum. And the reason this is necessary is because of what Ethereum is. So Ethereum, as we know, is a decentralized open source public blockchain-based platform which supports smart contracts. And the operative word in this definition is public. And while we have discussed previously what a public blockchain entails, let us contrast a public blockchain with a private one in order to truly understand its meaning. So we have discussed that a public blockchain network is one which has truly open membership. Anyone with the requisite hardware and software can join the network. Private blockchain networks, on the other hand, restrict who can join, and they usually have some kind of vetting process before someone is allowed to join the network. With public blockchain networks, there are typically plenty of nodes, and this is thanks to the open nature of its membership. Conversely, private blockchain networks have fewer nodes, partly due to the higher bar for their entry into the network. Public blockchain networks, due to the sheer number of nodes, take longer to arrive at a consensus. This is because there are more verification processes to be followed in a public network when you don't trust the other nodes completely. This is not the case with private blockchain networks in general, though, and this is why they are faster to converge on a consensus. Due to the lack of vetting for the nodes before entering the network, there is a higher likelihood of fraud in a public network, whereas this is typically not the case in a private blockchain network. We will now continue looking at each of the steps involved in transaction verification on the Ethereum network. Previously, we have taken a look at how the identity of the sender of a transaction can be verified by the use of digital signatures. We now take a closer look at another step in the transaction verification, which is to check whether the sender of the transaction has enough Ether in their accounts to see the transaction through. That is, we verify the account balance of the sender. So when performing the verification of a transaction, there are at least 3 different steps involved. One of these is to verify the sender of the transaction's identity and also the integrity of the transaction. And we previously saw how the use of digital signatures allows us to achieve this end. Any transaction which performs a write operation, whether on a smart contract on the Ethereum blockchain, will require the transaction initiator to pay some Ether. So one of the transaction verification steps is to confirm that the sender does indeed own enough Ether to send over in the transaction, whether to a recipient or to the mining node in order to see the transaction through. And a third check in the transaction verification is to confirm that the transaction is indeed a newly minted one and is not simply a replay of an old transaction. And this is done by means of a transaction nonce. In this clip, though, it is the second of these verification steps which we will zoom into, and that is to verify the balance in the account of the sender. When someone initiates a transaction on the Ethereum network, that transaction must go through an account. And as part of the verification, one must confirm that the account has enough balance in Ether to cover at least 2 things. If the transaction involves the transfer of Ether to another account, then the verification must check that there is enough Ether balance in the originator's account to cover this transfer. However, it is not just this Ether transfer which needs to be accounted for, but the cost of the transaction itself. Any transaction which is invoked in Ethereum has an associated transaction fee, and we have seen previously in this learning path that this transaction fee is a product of the gas consumed by the transaction and the value of the gas price which has been set when the transaction was invoked. However, another value can be set when the transaction is created, and this is the gas limit. This is done to impose a hard ceiling on the amount of gas which a transaction can consume as part of its execution. In case the gas limit is hit, then the total amount of Ether which the transaction sender needs to pay out is the gas limit multiplied by the gas price. So the transaction verification needs to ensure that the transaction sender has enough ether to cover this cost. Previously, we have taken a look at the mechanics of verifying the identity of the transaction sender and in checking for the transaction's integrity. It is now time for us to take a closer look at the process behind confirming that the sender does indeed own enough ether for the transaction to go through. So we clearly need some mechanism to check how much ether is owned by every account in the Ethereum network. And this is accomplished by means of a state database, which is maintained by every full node in Ethereum. So what does the state database look like? Well, in a highly simplified form, it will simply be a collection of key and value pairs, where the key will be the account addresses and the corresponding values will represent the ether balance in each of those accounts. So when the mining nodes in Ethereum need to verify each transaction, they will first check how much ether is being transferred by the sender to a recipient, and to that they will add the product of the gas limit and the gas price. That sum should be less than the ether balance in the account of the transaction originator. The value of ether being transferred, the gas limit, as well as the gas price will all be available in the transaction body, and the value of the ether balance can be obtained by a simple lookup in the state database. So with all of that information in hand, every mining node in the network will be able to confirm whether the sender of the transaction does indeed possess enough ether to see the transaction through. If this verification step fails, then the miner will simply drop that transaction from their own set, and the transaction originator will be notified that they do not possess enough gas for the transaction to be executed. We now continue zooming in on each of the steps involved in transaction verification on the Ethereum network. The last step we will be taking a look at is verifying the transaction nonce. Previously in this course, we took a look at how we can verify the identity of the transaction sender and then also confirm the integrity of the transaction itself by using digital signatures. We then saw how we can make use of the state database in Ethereum to verify that the sender of the transaction has enough ether to pay off the transaction execution. And the third step we will now be taking a look at is to check the nonce of the transaction, which will confirm that the transaction we are looking at is a new one and not simply a replay of an old transaction. So what exactly is meant by the term nonce? This is short for number used once. So a nonce is something which is used for a one-off event. That is, it is used exactly once and never again. In the context of Ethereum transactions, the transaction nonce is a unique integer ID, and this is something which is associated with every account in Ethereum, and it is incremented by 1 each time that account is used to initiate a new transaction. Just to clarify, the transaction nonce is a unique integer ID in the context of transactions originating in a single account rather than being unique across Ethereum. So the transaction nonce is in effect a transaction counter for a particular Ethereum account. Much like the ether balance for each Ethereum account, the nonce of the account is something which is maintained by each and every full node participating in the Ethereum network. So this is also part of the state database of Ethereum. And since this is in effect a transaction counter, it is something which is incremented by 1 for each transaction originating from the account. Even if a transaction were to fail verification or is never picked up from the transaction pool, this nonce value is not rolled back and can only be incremented. And this brings us to some of the rules when it comes to generating nonces for each account. These are the rules which must be followed by the full Ethereum nodes, since they are the ones tasked with the responsibility of maintaining the account state, which includes the account nonce. So the first of these rules is that the nonces must be generated in order. So a new nonce value cannot be less than any of the previous nonce values. And in addition, when the nonce is incremented, it must be in unit increments. So a nonce value of x should be followed by a nonce value of x plus 1 and then by x plus 2 and so on. So just to reiterate, this nonce value serves as a serial number or a transaction counter for the transactions originating from an account. So why exactly is this nonce used? Well, for one, it does perform an ordering of the transactions originating in an account. So if you would like to view all the transactions which have been invoked from a particular Ethereum account, the nonce value will allow you to order them in terms of time. While this use of the account nonce is something which provides us with some convenience, the nonce also serves a security purpose. That is, it prevents the deduplication or the double counting of transactions. To explain exactly how this works, I'm going to make use of an analogy where the nonce, which is associated with a blockchain transaction, can be compared to the check number involved in a bank transaction. So if we look at an Ether transfer transaction in Ethereum, we see that this includes the sender of the transaction, the recipient, the value being transferred, as well as the transaction nonce, which is the nonce associated with the sender's account. You will observe that any check transaction involving banks is also similar. There will be an entity issuing the check, which is similar to the sender here. The recipient is the equivalent of the check payee. The value which is being transferred in this case is equivalent to the value being paid out in the check. And finally, the transaction nonce in a blockchain transaction is analogous to the check number in any check transaction with banks. So what is the security purpose which is served by this transaction nonce or the check number? Well, for that, consider that a sender C has given a check to a recipient D, and this check has been issued by the sender's bank R. Now, let us say this recipient of the check is not the most trustworthy of individuals and also happens to have multiple bank accounts. He maintains an account with Bank X, Bank Y, and Bank Z. Since these days, you don't need to physically deposit a check, and you can simply take a picture and then deposit it electronically in any bank account, we consider the case that this recipient first deposits the check to the Bank X electronically. So far, this individual's actions are legitimate. However, he now tries to pull a fast one by depositing the check in two of his other bank accounts, in Bank Y and Bank Z. His hope is to get paid 3 times as much as he should by making 3 separate deposits with the same check. So the question is, will he get away with it? And the answer is a resounding no. This is because the banks Y and Z will be able to catch that this check has been deposited previously. And this is thanks to the serial number which is associated with any check. For any check transaction to go through, the bank which is accepting the check deposit will first check with the issuer's bank whether the check has been previously deposited somewhere, and they will be able to identify the check using the account of the check sender as well as the check number itself. The issuing bank will then be able to notify the other banks that this check has been deposited previously and should now be considered null and void. So when it comes to bank transactions involving checks, we can see that check numbers are able to prevent the double deposit, or in this case even a triple deposit, of the same check. And switching back now to the world of Ethereum, the transaction nonce plays the exact same role as the check number in the banking world. So if a sender C invokes a transaction involving the transfer of X Ether to the recipient D, this transaction will have the account nonce attached to it, which is 0123. Remember that this nonce is associated with the account of the sender. Any transaction initiated in the Ethereum network will be broadcast to every single mining node and will also make its way to the recipient D. This recipient will have a signed transaction, just as in the banking world, a recipient will have a signed check. Just as in the banking analogy, we saw that a recipient could try to deposit the signed check in multiple accounts. This recipient in Ethereum may try to replay the signed transaction by reintroducing it into the transaction pool. Now, once this transaction has been broadcast to the network, they will then compare the transaction nonce with the account nonce associated with the sender's account. If the transaction nonce happens to be less than the value of the account nonce which they have maintained in their state database, they will know that this transaction is simply a replay of a previous one, and they will simply disregard it. On the other hand, if the nodes notice that the nonce in the transaction is greater than the nonce associated with the sender's account in their own state database, they will consider that this transaction is verified, and the recipient D will stand to obtain the ether which has been transferred over in the transaction. So we now know that the use of the transaction nonce effectively works as a check number, and it prevents replay attacks in the Ethereum network. In this exercise, you will first enumerate the steps involved in the verification of a transaction. Once a transaction has been invoked and then thrown into the transaction pool, then many mining nodes will be able to pick them up, and then before they can potentially be added to the blockchain, they will need to be verified. You will need to recall what exactly are the steps involved in this verification process. For the next task, you will describe the ideal cryptographic hash function. We have seen in this course how the concept of cryptographic hashing has been used extensively in blockchain networks, and this is because there are a few properties of cryptographic hash functions which make them ideally suited for use in a blockchain. You will need to identify what those are. For the next task, you will compare the implementation of a centralized ledger with that of a distributed one. We have seen that blockchains are in effect distributed ledgers which are maintained by a number of different nodes. There are clearly some benefits to this approach given its use in blockchain networks. However, there are a few drawbacks as well. You will identify exactly what those are. And finally, you will distinguish between public and private blockchain networks. So Ethereum is an example of a public blockchain network, and there are certain properties which make it one. You will note down exactly what those properties are and how they contrast with the properties of private blockchain networks. Each of these topics were discussed during this course, so please pause this video and then take some time to perform each of these tasks on your own. For the first task in the exercise, you needed to recollect the various steps involved in the verification of a transaction after it has been picked up by a miner from the transaction pool and before it gets added to the blockchain. So one of the crucial verification steps is to verify the identity of the sender of the transaction. So one needs to be able to authenticate the sender so that we know for sure who it was who invoked the transaction. In addition, once we have identified the sender, then there is no way that the one who invoked the transaction can deny having initiated it. The way authentication and non-repudiation are implemented in the Ethereum network is by means of digital signatures. So what this step ensures is that only someone in possession of the private key of the sender could have initiated this transaction. One more verification step, which also involves the use of digital signatures, is to confirm the integrity of the transaction. That is, once the transaction has been invoked by the sender, it has not been modified in any way before it is mined. And in addition to knowing who sent the transaction and that it has not been tampered with, it is important to know that the one who invoked the transaction does indeed possess the assets which are being transferred over to a recipient. So if the transaction involves the transfer of ether from the sender to the recipient's account, then a quick lookup of the state database can be done to see whether the sender's account has the ether balance to make this transfer happen. Another piece of data which is also available in the Ethereum state database is the nonce of the sender's account, which is added to the transaction. This nonce is effectively a count of the number of transactions which have been initiated from the sender's account. Verifying this nonce value is necessary to ensure that the transaction which is currently being processed happens to be a new one and is not simply a replay of a previous transaction which some malicious party has thrown back into the transaction pool. For the next task, you needed to note down the properties of an ideal cryptographic hash function. So the cryptographic hash is a function extensively used in the Ethereum network. And one of the reasons for this is that it is very easy to compute a hash value from the input message. Given how frequently hashes are performed in Ethereum, it is important that the computation of this function is quick and not very resource intensive. Another important property of a cryptographic hash is the low likelihood of hash collisions. A hash collision occurs when multiple input values hash to the same output value. While this may be acceptable in many different situations, it is important for a cryptographic hash to have a rather wide range of output values and for there to be a rather wide distribution of the inputs to the outputs. And one of the reasons for this takes us to the next property of the ideal cryptographic hash, which is that it should be impossible for anyone to recreate the original input message when given only the hash output. In other words, if someone has presented to you a hash output, it should be impossible for you to reverse engineer it and learn of the input to the hash function which generated this output hash. Next, you needed to contrast the approach of using a centralized ledger versus using a distributed one. So the use of a centralized ledger means that all of the records in the ledger are stored on a single machine. Any node which needs access to the data on this ledger will need to establish a connection to this machine and then retrieve its records. Such a setup is relatively simple to implement since there is just a single machine which holds all the data. However, the problem with it includes that there is a single point of failure. If the node holding the ledger were to fail for some reason, then none of the nodes will have access to the data. In addition, there are also performance issues, and this can especially be seen from the nodes which happen to be geographically far away from the central ledger node. There could be significant network latency issues, and this will especially be felt if data needs to be retrieved from the ledger repeatedly. In contrast, when using a distributed ledger setup, there will be multiple nodes which maintain a copy of the ledger. A great benefit of this method is that the data is immediately accessible to each of the nodes, and they don't potentially need to go halfway around the world to retrieve the information. The distribution of the ledger data also ensures fault tolerance. Even if one or few of the nodes in the network were to go down, all of the other nodes have their own copy and can still access the data. However, one issue with any distributed system is that there needs to be frequent communication between all of the nodes to ensure the consistency of their own ledger data. Moving now to the final task in the exercise, where you needed to distinguish between public and private blockchain networks. Starting with public networks, of which Ethereum is an example, the membership to such a network is truly open. Anybody with the required hardware and software will be able to join the network. As a result, there are a large number of nodes typically in a public network, and a consequence of that is that it is typically slower to converge on a consensus. There is also a higher probability of fraud because the open nature of this network means that there is no vetting of the participants beforehand. On the other hand, when it comes to private networks, membership is restricted. So there may be some selection criteria before you can join such a network. A consequence of that is that there are typically far fewer nodes than in a public network, and that in turn affects the speed at which a consensus can be reached among the nodes. When there are fewer nodes involved, consensus can be reached far more quickly. And finally, given that there is usually some vetting process before anyone can join the network, the likelihood of fraud is much lower than in a public network. The likely scenario is that many other transactions will have been broadcast to the nodes simultaneously and will then be dropped into the transaction pool, which all of the mining nodes in the network will have access to. Out of all the initiated but unverified transactions in the transaction pool, the mining nodes will then pick up some subset of these transactions, and those transactions which have a high gas price set to it are much more likely to be picked up by a miner than those with lower gas prices. As a result, the subset of the transactions picked up by the mining nodes will have significant overlaps. However, one thing which is likely to vary a lot is the order in which the transactions have been picked up. So with all the different permutations of transactions and their ordering available among all the mining nodes in the network, how do all of these nodes arrive at a consensus on what the final content of the transactions and their ordering should be when the next block is written out to the blockchain? We start off by picturing all of the nodes which are participating in the blockchain network. Each of these nodes will map to at least one account in Ethereum, and these are the accounts which can be used in order to initiate transactions. So let us say that node C wants to send over some Ether to node D. This transfer of Ether will occur from C to D. However, when any transaction is initiated, because Ethereum happens to be a public blockchain network with a number of different nodes, the transaction will in fact be broadcast to the entire blockchain network. However, it is highly unlikely that such a transaction will exist in isolation on Ethereum. The likely scenario is that many other transactions will have been broadcast to the nodes simultaneously and will then be dropped into the transaction pool, which all of the mining nodes in the network will have access to. Out of all the initiated but unverified transactions in the transaction pool, the mining nodes will then pick up some subset of these transactions, and those transactions which have a high gas price set to it are much more likely to be picked up by a miner than those with lower gas prices. As a result, the subset of the transactions picked up by the mining nodes will have significant overlaps. However, one thing which is likely to vary a lot is the order in which the transactions have been picked up. So with all the different permutations of transactions and their ordering available among all the mining nodes in the network, how do all of these nodes arrive at a consensus on what the final content of the transactions and their ordering should be when the next block is written out to the blockchain? The short answer is that they make use of a consensus algorithm. And in the context of consensus algorithms on Ethereum, there are two of which we need to take a look at. The first of these is the proof of work consensus algorithm, which at the time of this recording in March 2019 is the one which is currently being used. This is used to achieve a consensus among nodes which do not trust each other. Similarly, there is also an algorithm called the proof of stake algorithm, and this is something which the developer community in Ethereum is actively trying to implement and may be the one in use while you're viewing this video. The proof of work algorithm does achieve its goal of achieving consensus in a trustless network. However, there are severe drawbacks. It is these limitations of the proof of work algorithm which proof of stake seeks to address. And in the following clips, we will take a look at exactly what the proof of work algorithm is, what its limitations are, and how the proof of stake algorithm can deliver all of the benefits of proof of work while mitigating its drawbacks. We will now take a look at the algorithm which is in use in the Ethereum network in order to achieve a consensus among all of the nodes on what the contents of the next block to be added to the blockchain will be. This is known as the proof of work algorithm, and this is one which is also in use on the Bitcoin network. So let us begin. So as discussed previously, there are two consensus algorithms which we must discuss in the context of Ethereum. The proof of work algorithm, which is currently in use as of this recording, and the proof of stake algorithm, which Ethereum might migrate to in the near future. In this course, we will take a detailed look at both of these algorithms, but first, we will start off with the proof of work algorithm. We have touched upon the fact that all of the mining nodes will come up with their own set of transactions in a particular order, and all of these are candidates to be the next block of transactions to be added to the blockchain. Out of all of the mining nodes, one of them will be selected as the one who will write the next block to the blockchain. Being selected as a successful miner, though, is something which is regarded as a privilege in Ethereum, and this is by no means a right. And Ethereum seeks to be that ideal world in which any privilege is something which needs to be earned, and this is earned by doing some work and then proving that you did that work. And as you may have guessed, it is the proof of work consensus algorithm which allows an Ethereum node to prove that it has performed some work in order to earn the privilege of writing the next block to the blockchain. So to explain exactly how this algorithm works, we start off by visiting our unverified transaction pool. So once transactions have been initiated on the network, they will make their way to this pool of unverified transactions, which are accessible to every single mining node in the Ethereum network. And since I've used the term a few times, you may ask, what exactly is a mining node in Ethereum? Well, the process of generating the proof of work in Ethereum is known as mining, and all of the Ethereum nodes which participate in this process are known as miners or mining nodes. Now, every single node in the Ethereum network need not be a miner, but for this example, let us assume that is the case, where we have our Ethereum network with 6 nodes A through F, and we assume that all of these 6 nodes happen to be miners. So going back now to our transaction pool, we have a whole host of unverified transactions over there, and all of the mining nodes will pick up some subset of these transactions, and an important factor in their consideration of which transactions to pick up is the gas fee. In the example you see on the screen in front of you, 4 of the miners have picked up some of the transactions from the pool, and you will notice that there is some overlap on the transactions. While there may be significant overlaps in the transactions picked up by all the miners, what will tend to vary significantly is the ordering of those transactions. But once a miner has been selected as the one to write the next block of transactions to the blockchain, it'll get to pocket all of the fees associated with those transactions included within its block. So when a transaction has been initiated by someone in the network, they will set a value of a gas price, and this is something which is used to incentivize the miner to pick up that transaction. So what exactly is the gas price? Well, let us revisit the concept of gas in Ethereum, and we have covered the fact previously that this is a measure of the computation work which is required in order to execute and verify a transaction. A more complex transaction will require more gas in order to see it through. When any transaction is invoked in the Ethereum network, the initiator needs to set a value for the gas price. This is a value which the initiator is willing to pay for every unit of gas which the transaction needs in order to execute. When an initiator sets a high gas price value, they are saying that they're willing to pay more per unit of work which the successful miner needs to perform. So while the gas price is a value which can be set by the transaction initiator, the total gas needed for the transaction may not be that easy to determine. This is because a transaction involves the execution of code, and there may be several conditions which are checked in the code before proceeding. So the total gas consumed by the transaction may depend on the outcome of those condition checks. As a result, the total gas consumption is not quite predictable, which is why the transaction initiator may choose to specify a gas limit. This is a way in which the one who invokes the transaction can impose a hard limit on how much gas can be consumed for the transaction to execute. This limits the amount which the transaction originator will have to spend for the transaction. However, if the gas limit has been hit and the transaction has not completed, then that transaction will be rolled back and the transaction originator will have to pay the amount up to the gas limit. And while it may be difficult to predict beforehand exactly how much gas will be needed for a transaction, it is possible to make an estimate. So every mining node in the Ethereum network must run the Ethereum virtual machine, or EVM. The EVM, as we have touched upon, is a common runtime environment, and this is required in order to execute the code of a smart contract. This is something which is required during the verification stages of a transaction, and among other things, the EVM is able to make an estimate of how much gas will be consumed by a transaction. So now we know that when a transaction has been invoked in the Ethereum network, there is a gas price field which is attached to it, as well as a gas limit. And there will be a number of different transactions with an associated gas price, which are in the unverified transaction pool. And out of these transactions, the miners will pick up a few of them. But looking at it from the miner standpoint, which of these transactions should be picked up? Well, the simple answer is the one which pays the most. So the total transaction fees which a miner can gain from a transaction is the product of the gas consumed by the transaction and the gas price which was set when the transaction was invoked. If a miner has been selected as the one to write the next block to the blockchain, they get to pocket all of the transaction fees associated with every transaction in their block. As a result, they are incentivized to pick those transactions from the transaction pool which have a higher gas price attached to it. And once the miners have picked up a set of transactions in a particular order, they will all enter into a competition in order to be selected as the miner to write the next block of transactions to the blockchain. As part of this process, they will need to perform a verification of the transactions. And once they do that, they will not only have a collection of verified transactions, but they will have a specific ordering of them. One important thing to keep in mind as far as transaction verifications goes is that this is a process which has intentionally been made very difficult. This is so that miners who perform transaction verifications must incur significant costs to do that, and this is something which is done to prevent malicious nodes from taking control of the Ethereum network. Now, let us summarize each of the steps involved when it comes to processing and verifying transactions. So when someone initiates a transaction on Ethereum, it goes into a pool of unverified transactions. From the transaction pool, every mining node will take out some subset of those transactions, and those transactions which have a high gas price attached to it are more likely to be picked up here. Following that, each miner has some set of transactions in a particular order and will then go on to verify each and every one of these transactions. Following that, every miner will then need to do some work and then submit some proof that they have performed the work. This will earn them the privilege of writing the next block of transactions to the blockchain and pocketing all of the transaction fees associated with the transactions within that block. Now the question arises, what exactly is the work which the miners need to perform? And the answer is, they need to find the proof of work nonce. This proof of work nonce is a number which fulfills some arbitrary and difficult condition, and it can only be found by trial and error. In the next clip, we will see exactly what that is. In the previous clip, we saw that the mining nodes in an Ethereum network will pick up some transactions from the transaction pool, will then order those transactions, and then verify them. After that, the miners will then compete in order to see who earns the privilege of writing the next block of transactions to the blockchain. The competition for the miners is finding the proof of work nonce. That miner which is the first to find this proof of work nonce wins that privilege of writing the next block. So what exactly is involved in finding this proof of work nonce? Well, for that, let us take a look at what exactly a particular block for a miner will contain. This will include the hash of the previous block in the blockchain and also a hash of the current set of transactions. This will include the root for the Merkle tree of the transactions. Note here that since every single miner will have a different set and ordering of transactions, this transaction hash will be different for every node. There will also be some additional metadata in the block, and right at the very top, the block also includes a proof of work nonce. Now all of this data is fed as input to a hashing function, and the output of the hashing function will be a block hash. Now we come to the proof of work part. It is not just any block hash which is acceptable to Ethereum, but this block hash must fulfill a condition. Specifically, it should be less than a specified target hash value. The miner, which is the first to compute a block hash which fulfills this condition, will be rewarded with the privilege of writing the next block to the blockchain. Now, it is very unlikely that a miner will be able to get a block hash fulfilling this condition at the first attempt. And since you cannot reverse engineer a hash output, that is, work out what input is necessary in order to produce a given hash, what a miner will need to do is to keep tweaking the inputs to the hash function until it generates a block hash which fulfills this condition, which along with the other block data is able to generate such a block hash. In other words, we need to find a nonce value which satisfies an arbitrary and difficult condition. That is, it should be used to generate a block hash which is less than a target hash value. So the term nonce is something which we have come across previously in this learning path. We had discussed that nonce is short for number used once, and this is something which is generated for a one-off event. The specific nonce which we had discussed earlier on was a transaction nonce, and this is a value which is associated with an Ethereum account. It effectively serves as a counter for the number of transactions which have been initiated from that account, and it is an integer value which is incremented by 1 for each new transaction invoked from that account. Now, this transaction nonce is in fact very different from the proof of work nonce which we are discussing right now. The proof of work nonce happens to be a random number, and it is used when computing the hash of a block of a miner, and the hash which is generated needs to fulfill an arbitrary and difficult condition. Before we delve into more detail with regards to the proof of work nonce, let us zoom out a little bit and take a look at what exactly a blockchain is and how it is used to represent a distributed ledger in Ethereum. Every block in the Ethereum blockchain includes a hash of the previous block. Each of the blocks includes a number of records which represent the transactions on the Ethereum network. We have seen previously how breaking up a ledger into a number of different blocks makes it easier to store the data. However, in order to maintain an overall sequence of transactions, we need to arrange not just the transactions within a block in order, but need to have an ordering of the blocks themselves. Which is why the ledger which is stored in a blockchain network happens to be chained together to form a sequence of blocks, and this is exactly what a blockchain is. And when we visualize a blockchain, this is what it roughly looks like. Within each block is a hash of all of the transaction data which constitutes that block, and there is a hash of the previous block as well. However, this is not the only data which is included in each block. So if we were to zoom into one of the blocks here, we see that there is also some metadata for the block, and in addition, there is also the proof of work nonce which is part of the block. All of this block data will then be fed into a hashing function, and the output of that function will be the block hash. And as we have discussed already, this block hash must fulfill an arbitrary and difficult condition. And what exactly might this condition look like? Well, an example is that the block hash must contain a certain number of zeros in the prefix. So for example, Ethereum may set a target hash which starts with 5 zeros, and it is up to the miners to come up with a block whose hash value is less than this target hash. A property of hash functions is that it is impossible for us to reverse engineer the input. That is, if we know what our desired output is, there is no way for us to figure out exactly what the input should be, and the only way for us to get the desired output is by tweaking the input by trial and error. So how exactly can we tweak the input to the hash function? Well, within the block we have the hash to the previous block, and this is something which cannot be altered since it is constant for all of the mining nodes. There is the block metadata, which cannot really be changed either. So the only things which a miner can change are the transactions which are included in the block and the proof of work nonce. So remember that the transactions are ones which need to follow a verification process, which is why the miner cannot simply come up with some bogus transactions. However, one thing which the miner can play around with, and which is far simpler to do than altering the transactions, is to try out different values for the proof of work nonce. So at first, a miner may try a value of 1234, and let's just say this produces a hash value for the block of 003567. The condition to check now will be whether this is less than the target hash value, but this condition will not be fulfilled if the target hash has, for example, 3 zeros in the prefix. When this happens, the only recourse for the miner is to try a different value for the proof of work nonce and then compute the hash of the block again, and then check once more if the hash output happens to be less than the target hash. And once again, given the inability to reverse engineer a hash function, the only way to do this is by trial and error. There is no intelligent way to figure out what the correct value for the proof of work nonce should be. So this miner tries one more time with a different value of the proof of work nonce, and once again, the output hash is not less than the target hash. So every miner will keep repeating the process until eventually one of the miners in the Ethereum network will find a proof of work nonce which fulfills this condition. One thing to keep in mind is that since every single miner will have a different set of transactions and ordering within them, the transaction hash within each of their blocks will be different. As a result, the transaction nonce which works for one of the miners will not necessarily work for another. So while all of the miners are participating in the same competition to find a proof of work nonce, each of them has a different path to victory. And the path for the miners is to keep trying randomly for different values of the proof of work nonce until the block hash fulfills this arbitrary and difficult condition. In the next clip, we will take a look at what exactly happens when one of the miners in the network becomes the first to find the proof of work nonce for its own block. In the previous clip, we saw how all of the mining nodes in the Ethereum network will be competing to find a proof of work nonce which fulfills an arbitrary and difficult condition. We now take a look at what exactly happens after a miner has found a valid proof of work nonce for their block. So once this proof of work nonce has been found, it is time for the miner to claim their prize. So each miner in the network, as we saw, is searching for its own proof of work nonce, and this is because each miner is likely to have their own set of transactions in their own order. So the consequence of that is that even though all of the miners are participating in the same competition, all of them are effectively running their own race. But once one of the miners happens to find a valid proof of work nonce, then it will quickly broadcast this news to all of the nodes in the network. It is then up to all of the other miners to stop what they're doing, that is, finding their own proof of work nonce, and then verify whether this miner who has announced themselves as the winner did indeed correctly calculate the proof of work nonce. Once this verification is complete and it has been confirmed that the miner did indeed correctly solve the proof of work puzzle, then it stands to pocket all of the associated rewards. This includes the transaction fees for every single transaction which was included in its block, and the transaction fee is calculated as the gas price quoted in the transaction multiplied by the gas used by that transaction. In addition to getting to keep the fees for each of the transactions, the miner will also be given some freshly minted Ether by the Ethereum network. So this is from the point of view of the winning miner, but what about all of the others in the network? Well, the short version is they simply need to fall in line. So while the miners are solving their own proof of work puzzle, they may receive a broadcast from one of the other miners in the network that they have successfully solved it, and then they are claiming their own prize. At this point, the miner then needs to stop searching for its own proof of work nonce and then switch over to verifying the claim of the miner which has announced itself as the winner. This process will involve verifying every single transaction in the claimant's block, and then they will generate a hash for the entire contents of the block, which includes the transaction as well as the proof of work nonce. They will then verify whether the block hash is less than the target hash value, and once this confirmation has been obtained, they will need to update their own chain with the contents of this block which they have just verified. They can then stop searching for the proof of work nonce since they already know that they have lost this particular round, and then they can move on to mining the transactions for the next block. Now, all of this reflects the behavior of an honest node in the Ethereum network. What if the node is not quite so upright? What if it chooses to ignore the message which has been broadcast by a claimant and then deny them of their rightful reward? Well, in the Ethereum network, ignoring such a message has a cost. This is because all of the other nodes in the network, assuming they are all honest, will have updated their own blockchains with the block which was broadcast by the node which claimed itself as the winner and was successfully verified. So if all of the nodes in the Ethereum network have one version of the blockchain and one particular node maintains a different version, it will be out of sync with its peers. And also, very importantly, it will lose any opportunity of claiming mining rewards in the future. Given each block in the blockchain contains the hash of the previous block, if this particular dishonest node has a different block in its copy of the blockchain when compared to the others in the network, then all of the subsequent blocks will also be different. So even if this dishonest block were to successfully solve the proof of work puzzle in one of the subsequent rounds, when the other miners will be verifying its claim, they will notice that this node has a different hash of the previous block and will reject its claim. So the reason why this proof of work puzzle is something which works for the Ethereum network is because the verification of the nonce is almost trivial. All of the nodes performing the verification will verify the individual transactions, but following that, computing the block hash and then verifying that it is less than the target hash value is a rather simple operation. On the other hand, finding a proof of work nonce which fulfills the condition is a very, very difficult problem. And this is something which involves a lot of work. And this is precisely the work which the mining nodes will need to perform at every iteration. And if they successfully find the proof of work nonce, they will need to broadcast it to the network in order to claim the prize. By now, we should have a fairly good understanding of what the proof of work algorithm involves and how exactly that is used in order to obtain a consensus among all of the nodes in the Ethereum blockchain network. In this clip, we will take a look at some of the flaws in the proof of work algorithm and how Ethereum is looking to replace it with a proof of stake algorithm for consensus. So far, we have studied the proof of work consensus algorithm and have seen how this can be used in order to achieve a consensus among nodes in the Ethereum network which do not trust each other. There are, however, several drawbacks to the proof of work algorithm, which is why Ethereum is actively looking to replace it with the proof of stake algorithm. So, what exactly are the problems with the proof of work algorithm for consensus? Well, we have discussed the fact that if there is a fraudulent node in the network, it may decide to ignore the correctly mined blocks and then create its own block of transactions itself and then add that to its version of the blockchain. Now, this particular node is at risk of falling out of sync with the other nodes in the network, and if it tries to claim the mining price in any of the subsequent blocks during the verification process of that block, it will become evident to the other nodes in the network that this node is not working with a correct copy of the blockchain. However, consider a scenario where a fraudulent party does not control just a single node in the network, but a majority of them. In fact, there are several blockchain networks out there where the majority of the processing power in the network is controlled by just a handful of entities. If these entities were to gang up and then control more than a majority of the processing power in the network, well, then they can effectively corner the process, and at this point, they can just manufacture any kind of transactions and then verify their own fraudulent transactions. This is referred to as a 51% attack, and though this hasn't happened yet in any of the major blockchain networks, this is a real possibility. Another problem with the proof of work consensus algorithm, which is an ongoing one, is that every one of the miners in the network is looking to find the proof of work nonce. Given that the Ethereum network has over 25,000 nodes, all of them actively trying to find the proof of work nonce at the same time involves the consumption of a lot of electricity. In fact, the Bitcoin network also uses the proof of work algorithm, and among other things, it has been in the news for having these massive mining farms in parts of the world like Iceland, where electricity is very cheap and cooling costs for servers are low. Now, most of this energy consumption is a waste, and this is because out of all of the mining nodes which are consuming electricity to find the proof of work nonce, in the end, it's just one of these miners which will win the contest and earn the privilege of writing the new block to the blockchain. So the risk of being cornered by a handful of entities which control the network and the massive energy consumption of the proof of work algorithm means that Ethereum has been actively looking beyond it, and this is where the proof of stake algorithm steps into the picture. The Ethereum community has been actively looking at this proof of stake algorithm and, as of this recording, plan to implement it in the near future. This algorithm is designed to be less vulnerable to centralization, so even if a single entity were to control a majority of the nodes in the network and the majority of the processing power, they still won't be able to corner the network. Given that the proof of stake algorithm has not been implemented yet, the specific details of it are beyond the scope of this course, but I will try to summarize it very quickly. The nodes which wish to collect the transaction fees linked to any transaction will pick up transactions from the transaction pools and then form their own block of transactions, just as with the proof of work algorithm. However, rather than competing to find a nonce by trial and error, they will deposit some tokens into a central location. One of those tokens will be picked up at random, and the node which deposited that token will have the privilege of writing down the next block to the blockchain. So now that we understand how exactly a blockchain network comes to a consensus on what the state of the blockchain should be, let us review the capabilities of a blockchain network. We have seen that a blockchain network like Ethereum allows multiple parties to initiate transactions. In fact, anybody who joins the network has the ability to do so. In such cases, there is no need for a trusted or central authority to validate any transactions. By means of consensus algorithms, all of the nodes in the network are able to arrive at a consensus on what the correct transaction is, and what the state of the blockchain should be. And this is possible thanks to mechanisms such as the proof of work consensus algorithm, as well as the verification process, which is performed not just by the successful miner of the block, but all of the nodes in the blockchain network. One crucial aspect of a blockchain network is that all of the transactions are immutable. Once they have been written down to the blockchain, they cannot be overwritten or modified. If anyone does try to do this, however, they will eventually be caught. And one reason for this is that every participant in the blockchain network has access to the shared ledger. Many of the participants will retain and maintain a full copy of the ledger on their own. And if the copy of the ledger on any of the other nodes happen to differ with theirs, they will know that there is some fraudulent activity taking place. In this clip, we will be taking a look at one of the crucial features of the Ethereum network, namely its support for the notion of smart contracts. So what exactly is a smart contract? One definition which we have taken a look at previously is that it is a protocol to digitally specify, verify, or even enforce the terms of a contract. One way to think of it is that smart contracts in the Ethereum world are pretty much exactly the same as regular contracts, with the difference that smart contracts are digital. Rather than specifying the terms of a contract in legal terms as you would in a regular contract, with smart contracts, you write code. So now the question may arise, where exactly are smart contracts stored? Well, they are simply part of the blockchain network. In fact, smart contracts are part of the state of the Ethereum network. And in fact, just like with regular accounts in Ethereum, there are also contract accounts, which includes the state of the contract as well as the executable code. We can now take a look at why exactly smart contracts are useful and how they can in fact be superior to regular contracts. So consider as an example a campaign on the Kickstarter platform. Kickstarter, in case you're not aware, is a fundraising platform for ventures, and Kickstarter enables these ventures to be funded using the technique of crowdsourcing. So if there are supporters of a venture on Kickstarter, what they will do in order to fund that venture is to transfer over their money to Kickstarter itself. Kickstarter will keep for itself a portion of that money and then transfer over the remaining funds to the product team of the venture. So what has just happened here? Well, Kickstarter is a fundraising platform, and we have observed that it effectively works as a third party which sits between a product team which is looking to raise funds and the supporters who wish to contribute to it. So in this case, any product team which is looking to raise money for a venture will need to go up to Kickstarter and then create a campaign over there. The way Kickstarter works, money which is contributed by supporters towards a venture does not directly flow to that venture, but only if there are enough contributions to fully fund it will Kickstarter hand over the money to the product team. If not, the money will be handed back to the supporters. So in such a situation, the product team expects Kickstarter to pay them if the project is successfully funded, and the supporters want their money to go into the project. There is, however, one major issue with this setup. Specifically, both the supporters and the product team have to place their trust in the third party, which is Kickstarter. There is, however, an alternative to this. Instead of transferring over some funds to a trusted third party, what if the supporters of a venture handed their money over to a smart contract, which in turn transfers it over to the product team? So just like Kickstarter promises to hold the funds until a particular venture has been fully funded, the smart contract can be coded up in such a way that it serves the exact same purpose. It will hold all of the received funds until the funding goal has been reached. So the supporters of a particular project will be able to make their contributions, and their money will flow over to the smart contract. If the project is a success, that is, the funding goal has been reached, then the money will pass over from the smart contract to the product team. And if that target was not achieved, well, the money will simply go back to the supporters. In the case of a third-party crowdsourcing platform like Kickstarter, all this behavior will be written in their legal terms and conditions. In the case of smart contract, all of this is written in code. In the case of smart contracts, because they are stored on the blockchain network, everything is distributed and available for the public to view. In the scenario which I just described, where funds move from the supporters to the smart contract and then eventually may make its way to the product team, there was no single entity which was in control of the money. The funds were entrusted to the smart contract, which is controlled by the blockchain network as a whole. Which brings us now to some of the properties of smart contracts. Just like with blockchain transactions, smart contracts are immutable. If you'd like to change the behavior of an existing smart contract, you will need to create a brand new one. Another feature of smart contracts is that they are distributed in the blockchain network. So it's not just a single node which will have a copy of the contract, but all of the participating nodes will be able to access it. One benefit of the immutability of smart contracts is that once they have been created, they can never be changed again. They are effectively tamper-proof. And the distributed nature of these contracts ensures that when someone invokes one of the functions in that contract, it is the correct code which will be executed, since all of the participating nodes in the blockchain network will need to validate the transaction. As a result, what you see in the smart contract is exactly what will be executed, and there is no single entity which can force the contract to release funds, for example. So these smart contracts do seem rather interesting and seem to have a lot of uses as well. But how exactly do we create smart contracts? Well, we can code them up using a special programming language called Solidity. Though there are other languages in which we can code smart contracts, Solidity is by far the most well-documented and the most mature among the options. What exactly Solidity is and the features which it includes will be covered in the next clip. In the previous clip, we discussed what smart contracts are and how they can be coded up in order to specify the terms of a contract and potentially even enforce them. Smart contracts can be written in a number of different programming languages. However, one of these is by far the most popular and the most well documented, and this is the Solidity programming language. So let us take a look at that language and some of its features. So what exactly is Solidity in a nutshell? Well, we can describe it as a high-level programming language whose code compiles into the Ethereum bytecode. It is this bytecode which can be executed on any node which runs the Ethereum virtual machine. So just to summarize how that works, you will write your smart contract using the Solidity programming language. This is what you can use in order to specify the terms of a contract and even enforce it. Once you have coded up the contract, before it can be executed, it needs to be compiled, and the output of the compiler will be the Ethereum bytecode. It is the bytecode which is the binary version of the smart contract and can be executed. But for that to happen, it needs to be run using a special software, and this is the Ethereum virtual machine. Those of you who have some experience programming in Java will notice the similarities here. Java programs can be compiled to Java bytecode, and those can be executed on any machine which is running the Java virtual machine. The similarities with Java don't just end there, however. So let us now take a closer look at some of the features of the Solidity programming language. And this is to give you an idea of the building blocks which are available in order for you to code up your own smart contracts. So just like with many programming languages, Solidity allows you to add comments to your code. In addition, there are various types which are supported in Solidity. These include some primitive types such as booleans and integers, and there are also complex and user-defined types which one can specify. Logging in Solidity is supported by the means of events. In case some action has taken place, you can log those by recording them as events, and then you can build apps which can listen to specific kinds of events and then take actions accordingly. Just like with any high-level programming language, Solidity also includes functions, and there are different types of functions available depending on whether it performs a read operation or writes to the contract or the blockchain. In addition, Solidity also supports the concept of function modifiers. These are effectively checks for conditions which will decide whether the function should be executed or not. Solidity also happens to be an object-oriented language, and this supports the concept of inheritance. If you have any prior experience programming in C++, Java, Python, or any object-oriented programming language, then learning the Solidity language will not be difficult at all. However, it does have its own quirks and certain behaviors which are suited to a blockchain network, which you may need to get used to. We can now zoom in on some of these features, starting with the comments. So in Solidity, both single-line and multi-line comments are supported, and the syntax is similar to that of the Java language. We can quickly move ahead to types in Solidity, and here there are a lot of primitive types which are supported, which include booleans, integers, strings, and while these are the standard native types in Solidity, there are also some Ethereum-specific types. For example, there is an address type which is used to identify Ethereum accounts. As of this recording, however, there is no support in Solidity for floating point numbers. Moving along from the native types in Solidity, the language also supports structures, enumerations, as well as arrays. While arrays are used to store data of the same type, structs can be used to encapsulate data of multiple types. An important data structure in any programming language is one which can hold key and value pairs. And in Solidity, it is the mapping type which allows one to do this. Moving along now from types to events. So as discussed previously, this is the mechanism which is used by the Solidity language in order to log information. Events effectively serve as interfaces to the logs of the smart contract. Events, however, only allow the contract to write to the logs, and they do not have the ability to read from them. However, it is possible to build another application to read from the smart contract logs and then listen for specific events and potentially take action when a certain event is recorded. Moving along now to functions in the Solidity language, and these can broadly be categorized into two types, constant and transactional. Constant is when there is only a read operation which is performed, and a call to the function does not change the state of the contract or the blockchain in any manner. This does not invoke any transaction on the Ethereum network, so such operations don't consume any gas and there are no transaction fees to be paid. On the other hand, if the function call does modify the state of the contract or the blockchain, then a transaction will be invoked and you will need to pay transaction fees. This brings us along now to function modifiers, and these are effectively used to alter the behavior of a function in a smart contract. For example, these can be used to check for a certain condition, and if that condition is satisfied, then the execution of the function can go ahead. However, if the condition fails, then any code which is defined after the condition check will not be executed. From the example we saw in the previous clip, a condition to check would be whether a campaign has been fully funded before transferring the funds over from the smart contract to the product team who set up the campaign. So one thing to keep in mind with the Solidity language is that it is possible to inherit from smart contracts. Any functions which are defined within contracts with specific modifiers can also be inherited and potentially even overridden. So modifiers can be a useful way for you to aggregate a number of checks. And it's not necessary that a function should have just a single modifier associated with it, but you can have multiple modifiers linked to a function. This brings us along now to the concept of inheritance, and this feature is similar to other programming languages, and it is smart contracts themselves which can be inherited. So for example, it is possible for you to define a base smart contract and have a number of derived contracts which inherit from it and potentially override some of its behavior. We move along now from the features of the Solidity programming language to how it can be executed. So we have already touched upon the concept of Ethereum Bytecode, and these are the binary versions of smart contract which can be executed. This execution is handled by the Ethereum virtual machine. One feature of bytecode, however, is that it is not exactly human readable, and it cannot be used to determine, for example, how much gas will be consumed by a transaction. It is for this purpose that there are opcode versions of smart contracts as well. So this is something which is also output by most Solidity compilers, and these are effectively low-level human-readable instructions of the smart contract. So every smart contract can be represented as a sequence of opcodes where each individual opcode represents a single action. So while the Ethereum bytecode is something which is understood by the EVM, opcodes cannot really be interpreted in the same manner. However, they do have their hexadecimal counterparts, and since each opcode represents a single action, the opcodes can be used to determine the overall complexity of any operation on a smart contract. This is exactly why the opcode can be used to estimate the amount of gas which a particular transaction will require to be executed. It is the concept of gas which we will take a closer look at in the next clip. Previously in this course and in the learning path, we have discussed the concept of gas. In this clip, we will take a more detailed look at it and then see exactly how it is used in order to fuel a transaction. Gas, as we have discussed, is a unit which is used to measure the computational complexity of any operation in Ethereum. The more complex an operation, the more gas it requires to see it through to completion. In the last clip, we discussed the fact that any smart contract and the functions within it can be expressed as a sequence of opcodes, and each individual opcode translates to one action. Now, if you consider that gas is the fuel which is used to power a transaction, then every single operation which is expressed as an opcode requires a predefined amount of gas. For example, writing 1 byte of data to memory will require a certain amount of gas, whereas writing an entire array will require more. As you can imagine, any transaction will involve a sequence of read, write, and other operations, and each of these corresponds to the consumption of some amount of gas. When you sum up the gas requirements for each individual action in a transaction, then you get the total gas consumption for the transaction itself. This is why when any transaction is invoked in Ethereum, it must be provided with enough fuel to see it through to completion. Since many transactions will involve the check for certain conditions before execution, it is not always possible to know beforehand exactly how much gas a transaction will consume. As a result, one must always be conservative, and when invoking a transaction, must provide enough gas to cover the worst case scenario. In case you provide a transaction with a lot more gas than is necessary for it to execute completely, well, you need not worry because any unused gas will be returned back to the transaction originator. As a result, the gas which is supplied to a transaction can be thought of as analogous to the gas which is loaded in a vehicle. You will ideally load enough gas for the vehicle to reach its final destination, and if there is any gas left in the tank after the journey is complete, well, you can simply use it for the next trip. So the question to ask at this point is, what if there is not enough gas supplied to a transaction? Can it run out of gas? And the answer is yes. Transactions which do run out of gas are reverted. However, the originator of the transaction must still pay the transaction fee for the work which was done to process the transaction until the point it ran out of gas. We can once again use the fuel in the car analogy here. If the vehicle does not have enough gas in the tank to go all the way to the destination, then at some point it will run out of gas, and even though it hasn't reached its destination, the amount of gas which was consumed is lost, and whatever fee was paid for it is lost as well. This analogy, of course, makes the assumption that there are no gas stations along the way in which you can top up your fuel tank. We now move along to two concepts which are related to gas in Ethereum, one of which is the gas price, and the other is the gas limit. Both of these are values which can be set when originating a transaction. Let us now take a closer look at the gas price concept. This effectively translates to the amount which the sender of the transaction is willing to pay per unit of gas in order for the transaction to be executed. So if your transaction ends up consuming X units of gas, and you set a gas price of 10 Ether when invoking your transaction, then the total transaction fee which you end up paying will be 10 times X. So the total cost which you end up paying for a transaction is directly proportional to the value of the gas price which is set. So you can end up paying less for your transaction if you quote a lower gas price. And this can be done by varying the gas price field when you're invoking the transaction. So the gas price ends up determining your final transaction cost, and this is something which is clearly not a fixed amount. You can set a different gas price for each transaction which you invoke. And the unit which is used to express the gas price is the Ethereum cryptocurrency of Ether. More realistically, you will use one of the Ether subunits to specify the gas price. Specifically, you may express gas price in terms of Wei. So given a high gas price equates to a higher transaction cost, why exactly would one want to set a high value for the gas price? This is because a higher value of gas price means that a miner is more likely to pick up that transaction. Since the gas price translates to the amount a miner will get paid per unit of work, they will try to maximize the transaction fees which they get paid out by picking those transactions from the transaction pool which have a high gas price. Now, since gas price is expressed in the unit of Ether, let us take a look at this in a little more detail. So Ether is the name of the cryptocurrency which is used in the Ethereum network. Just as you would use euros in the Eurozone or the US dollar in the United States, in the world of Ethereum, you pay for services using Ether. And the service in Ethereum which you need to pay for are the computation of transactions. As mentioned, when specifying the gas price in any transaction, you will not express the price usually in terms of Ether, but in one of its subunits. Wei is the most commonly used subunit, and 1 Ether translates to 10 to the power 18 Wei. It does make sense to express gas price in terms of Wei because 1 Ether at the time of this recording translates to about 130 US dollars. And I can quote the US dollar price for Ether because this cryptocurrency can be bought for regular or fiat currencies. With that, we can move along now to the other element of gas, which is expressed in a transaction, and this is the gas limit. So the gas limit can be defined as the maximum amount of gas which the sender is willing to set for a particular transaction. Since it's not always possible to predict exactly how much gas will be consumed by a transaction initiator may want to protect against spending way more on a transaction than they're comfortable with. They can do this by setting a hard limit for the amount of gas to be used by a transaction, and when you multiply that by the transaction fee, you get the maximum amount of ether which will be spent for the transaction. Do keep in mind though that when the gas limit has been hit for a transaction, it means that it has not executed completely and it will be reverted. When invoking transactions on Ethereum, do keep in mind that by default, it sets a gas limit for all transactions to 21,000 gas. One thing to keep in mind when the gas limit has been hit and the transaction reverted is that all of the associated transaction costs will be lost by the sender. So by setting a gas limit for a transaction, you're effectively saying that you'd rather lose that money and not see the transaction through to completion than risk spending a lot more. So this gas limit in some ways can be thought of as paying out insurance premiums. This moves us to some of the other points to keep in mind when specifying a gas limit. As we have discussed, different operations on Ethereum all have different gas costs associated with them. While there are a number of different tools available to estimate the gas cost for a particular transaction just when you invoke them, these may not always be accurate, especially if there are a lot of checks for conditions in your transaction. So if you load up your transaction with a certain amount of gas, and if the gas is not enough for the transaction to see through to completion, then the miners will stop executing the moment the gas runs out and will still pocket the transaction fee for processing the transaction until that point. The effect of the transaction will still be reverted, however. On the other hand, if there is more than enough gas supplied to a transaction, and if there is gas left over, it will simply be refunded to the account of the transaction originator. In this exercise, you will first describe the proof of work consensus algorithm. In order to achieve a consensus among all of the nodes in the Ethereum network, the proof of work algorithm is the one which is in use at the moment. As the name suggests, however, this does involve a lot of work for the mining nodes. You will need to describe what exactly the work it is which they need to perform. For the next task, you will list the flaws with the proof of work algorithm. We discussed during this course that the Ethereum community is looking to replace the proof of work algorithm with the proof of stake algorithm in order to achieve a consensus. The reason for this is to address some of the big flaws with the proof of work, and you will need to list down what exactly those are. For the next task, you will identify some properties of smart contracts. One of the reasons for Ethereum's popularity is its support for smart contracts. So, what exactly are the characteristics of these smart contracts which make them so appealing? And finally, you will recall some of the functions of the gas price and the gas limit fields which are specified when invoking a transaction in the Ethereum network. Each of these topics were covered during this course, so please pause this video and then take some time to perform each of these tasks on your own. For the first task, you needed to describe the proof of work algorithm which is used by the Ethereum network in order to achieve a consensus. The proof of work consensus algorithm involves the mining nodes in the Ethereum network performing a task which has intentionally been made very difficult. The objective of this task is to construct a block which includes all of the data related to the transactions which the mining node has picked up from the transaction pool and then verified. The block should also include a cryptographic hash of the previous block in the blockchain, and there will also be some block metadata. And on top of all of that, there is also a field for the proof of work nonce. So once such a block has been constructed, the miner will produce a hash of that block, and this hash value must be less than a specified target hash value. If the block hash does not fulfill this condition of being less than the target hash, then the miner will need to change the value of the proof of work nonce and then recompute the block hash. This process will keep going on among all of the miners in the blockchain network until finally one of the mining nodes will have found a proof of work nonce which generates a block hash less than the target hash. This task is very difficult because it is not possible to reverse engineer the hash output to find the input values which will produce the desired hash. So the only way to fulfill this condition of finding a block hash which is less than the target hash is by trial and error, where the proof of work nonce value will need to be changed randomly until the block hash is less than the target hash. Another point to note is that there is not just a single correct answer. There can be multiple proof of work nonce values which fulfill this condition. And because each of the miners in the blockchain network will have their own list of transactions in their own order, each miner will need to find a different value for the proof of work nonce. So effectively, every miner is running their own race. However, when one of the miners has calculated a correct proof of work nonce which fulfills this condition, then they will broadcast it to the entire network, at which point all of the other miners will stop what they're doing and then verify this miner's claim. Which brings us now to the next task in the exercise, which was to identify the flaws with the proof of work algorithm. One of the biggest problems, which hasn't occurred yet, but it could be just a matter of time before it does, is that just a small number of miners can end up controlling the consensus. So if just a single entity or a handful of them who are colluding happen to control over 50% of the total computing capacity in the Ethereum network, then they can simply emit and then verify their own fraudulent transactions. Another huge problem with this proof of work consensus algorithm, and something which is ongoing, is its significant and intentionally wasteful consumption of energy. In the Ethereum network, all of the mining nodes will need to expend a lot of energy in order to find a valid proof of work nonce. Since the only way to do this is by trial and error, there will simply be a lot of random number generations going on, followed by the computation of the block hash, and then checking whether this is less than the target hash. And while all of the thousands of miners in the Ethereum network are performing this operation for every block, in the end, there will just be a single miner who will end up reaping the mining rewards. This proof of work is required in order to prevent denial of service attacks, where malicious nodes will simply overload the system with a lot of fake transactions and ask for them to be verified. However, these two significant flaws with the proof of work algorithm has led the Ethereum community to look at other options. This is where the proof of stake algorithm has entered the picture and could potentially replace the proof of work algorithm in the near future. Moving along now to the next task in the exercise, where you needed to list down some of the properties of smart contracts. Smart contracts are in effect digital versions of regular contracts. Within these, you can specify, verify, and even enforce contractual terms. The only difference between smart contracts and regular contracts is that in the smart version, the contractual terms are expressed in code rather than in some legal language. Given that Ethereum is a public blockchain network, this means that smart contracts are also public. They are in fact stored on the Ethereum network and are part of the state of the network. As a result, smart contracts are open for all to view. However, it is possible to code a smart contract so that only specific account addresses will be able to invoke transactions from it. And one of the greatest advantages of smart contracts is that they eliminate the requirement of a trusted third party for many transactions. So rather than placing your trust in a single third party entity to ensure that the contractual clauses have been adhered to, you end up putting your faith in the collective actions of the nodes in the Ethereum network. For the final task in the exercise, you needed to list down the functions of the gas price and gas limit fields when invoking a transaction. When it comes to the gas price field, this represents the price which the initiator of the transaction is willing to pay per unit of complexity of the transaction being invoked. the total transaction fee which will be paid by the initiator is directly proportional to this gas price value, and higher the value of this gas price, the greater the likelihood of it being picked up by one of the mining nodes. As for the gas limit field in a transaction, this effectively imposes a ceiling on the gas to be consumed for the transaction. By specifying this gas limit, the transaction initiator ends up limiting the ether which they will end up spending on that transaction. However, specifying a low limit increases the risk of this transaction not being seen through to completion. That is, this transaction may run out of gas. However, even if this gas limit has been hit, the transaction initiator will still need to pay out a transaction fee, which is equal to the product of the gas limit and the gas price.